Good afternoon, everyone. Am I audible?
Yes, we are audible.
Thank you, madam. So I welcome all the participants to day 4 of our E&ICT online faculty development program on optimization technique, theory, practice, and emerging application. In today's session, we will discuss about RAW algorithm. So there are three variants of RAW algorithm we are going to discuss. Moreover, these algorithms are extension of, you can say, TLBO and Joya algorithm, which we discussed in yesterday's lecture. After that, we'll see another lecture on artificial bee colony optimization algorithm, which will be taken by Dr. Manjuwala BC Madam. So let us start today's session with RAW algorithm. So first, before going to the RAW algorithm, some of the important aspect those people who are working in the field of soft computing or optimization method that you can find in the RAW algorithm introduction part, and some important message is given by Professor Rao that we will discuss. Then we will see the three variants of RAW algorithm, and we'll compare these three algorithms. We'll see what are the similarity in these three algorithms and what are the differences in these three variants of RAW algorithm. So you can see if you go to literature, like in my past lecture, somebody asked about which journal we need to focus. So there are several journals you can look into, like Swarm Evolutionary Computing, published by Elsevier, Applied Soft Computing, published by Elsevier, Soft Computing, published by Springer, and other journals, not limited to only IEEE or Elsevier or Springer. There are lot many journals are accepting the articles for soft computing algorithms or soft computing works. So if you go through these journals, you will find every year or every month, you can see every issue also, journal issue also, you will find new optimization algorithm. So these algorithms are mostly, if you see, they are improvement over the traditional algorithms, or they are hybrid algorithms. So they are mixing one algorithm with another algorithm. Like one of the example you can see, we have genetic algorithm and we have particle sum optimization algorithm. So if you see that some steps of genetic algorithm you can take and you can combine with some steps of the PSO and design a hybrid algorithm which performs better than the genetic algorithm as well as the PSO algorithm. Then you can write one article. Like that, people are developing, researchers are developing various hybrid algorithms. Okay, and they are contributing to the soft computing society. But the problem is that nobody is taking these algorithm further, right? Rather than they focus on the mixing one algorithm with another algorithm, but application perspective, like if you want to apply a structural engineering application or you want to apply a cryogenic application, right? So such type of applications are not there. So Professor Rao mentioned that there is no takers for the algorithms that are developed in each and every month, or which we call as new optimization algorithms. So it is a threat, research threat, and it is also shows that there is no advancement in the field of soft computing. So rather than focusing on the fundamental algorithms, people used to apply some kind of applications or some kind of hybridization of the algorithm without focusing on the basic of the algorithm, right? So he suggested that researchers should focus on developing a simple optimization technique rather than mixing one algorithm with another algorithm or applying in a particular application. Obviously, application has a merit. Many people applied various application by taking different algorithms, right? So effective solutions to the complex problem instead of developing metaphor-based algorithm. Genetic algorithm is a metaphor. Particle sum optimization is a metaphor. Differential evolution algorithm is a metaphor. Simulated annealing, end colony optimization. These all are very popular metaphors. So rather than focusing on this metaphor-based solution, we should focus on the simple optimization technique. Okay, so he suggested to contribute to the soft computing field by developing some metaphor-less algorithm, optimization algorithm, right? Not metaphor-based soft optimization algorithm. And like the teaching learning based optimization, where we have seen there is a teacher phase and there is a learner phase, or you can see in the Jaya algorithm, both phases are merged into a single equation in which we say that our objective is not to get success, but our objective is also to avoid failure. So we compare our solution, uh, solution with the base solution, as well as we are comparing our solution with the worst solution. So we have to be away from the worst solution, and we have to be very close to the best solution. So at a time, your objective to fulfill both. Most of the optimization algorithm we are looking that how we can reach to the best solution. We are not looking that how we will be away from the worst solution. That is also very much important, right? Both factor if you consider, then you can reach to the near to the global solution in a faster way, right? So these three optimization algorithms, which was developed by Professor Rao in the year of 2020. So these three algorithms are called as algorithm specific parameterless algorithm. You will not find any parameter like we have seen there is no parameter in the case of teaching learning based optimization, as well as there is no parameter in the Jaya algorithm. So in the similar fashion, here also you will not find any parameters. While you will discuss about the objective functions or you will do calculation, you will not find any parameter, right? So let us start the basics of this RAW algorithm. Then we will focus on RAW 1 and its implementation. And once you are okay with RAW 1 algorithm, then we will go for RAW 2 and RAW 3. And once you are comfortable in RAW 1, I request you, if you are comfortable to write code, you can also write the code for RAW 2 and RAW 3 as an assignment. Okay, like every optimization algorithm, here we have taken a function which we called as objective function, and we represent it by f of x. And you know our objective is to either to minimize this particular function or to maximize this particular function. Okay, like in the previous lecture, we have seen there is a Himal-Blau function, right? Our objective is to minimize that particular function, right? So here also we'll see one of the mathematical one, okay, mathematical function, right, which is called as on constant benchmark function. So we'll take on constant benchmark function of sphere, and for that we'll solve the problem using that particular problem using the RAW 1, RAW 2, and RAW 3 algorithm. Okay, so now you can see at any iteration I. Assume that we have m number of design variables. Yesterday class also we have seen, if you look into TLBO, in a particular class we have students, right? We have taken a small example with 5 different students. So number of student in a particular class is same as number of design variables, which we represent by m, right? Uh, these are nothing but your design variable. Design variables is, sorry, x1 and x2 are the design variables, right? So number of student is same as the number of candidate solution, which is equal to n. And how many subjects are studied by a particular student? Okay, that is called as your design variables. That is nothing but number of subjects, which we represent by m. So this m represents your number of subjects, n represents your number of students. Where you can see we say population size, right? We have taken n different population starting from 1, 2, 3 up to n. So same example you can take, right? There are 5 different students in your class. Each and every student is enrolled in 2 different subjects. The subjects are represented as X1 and X2, and 5 different students. You can say population 1, population 2, P3, P4, and P5. So if you take 5 cross 2, you can generate the randomly these particular values subjected to a particular range, right? For example, last class we have taken -5 is the lower limit for X1 and X2, and upper limit is +5, right? Now, out of these 5 population or 5 different students, definitely one student is the best student, right? And one student is the worst student. So we have used a variable best to keep the best value of f of x. Okay, the best students fitness function f of x. Okay, we are calculating f of x, right? So once you put x1, x2 value in f of x, you will get f of x value, right? By looking into f of x value, you can decide that which one is the best value. Similarly, you can plan which one is worst value, right? So we have taken a variable best which obtains the best value of f of x in the entire candidate solution. Similarly, we have taken another variable that is called as worst. That is the worst candidate obtains the worst value of f of x. Suppose it is a minimization problem, then you will see the minimum value out of these 5 values. If it is a maximization problem, you will see maximum value out of these 5 different values. So for a set of candidate solution, you have to determine best and worst. If you remember in Joya algorithm also, we are finding the same thing. What we are doing? We are finding the best solution. We are finding the worst solution. We are comparing our solution with the best solution and solution with worst solutions. We have to close to the success. At the same time, we have to avoid the failure. The similar structure is also followed here. Okay. Now, these are basic things related to if you have studied, you have understood the previous algorithm, it is clear to you. Now, here you can see 3 different equations that are used for 3 different variants of Rao algorithm. So, first equation is for Rao 1 algorithm. Second equation is for Rao 2 algorithm. Third is for Rao 3 algorithm. It looks very complex, but it is very easy, right? So let us see, understand what is the meaning of these equations. So here we have taken 3 different index. Like you can see here, we have written x, j, k, I. Right? You know, we have number of students, we have number of subjects, right? And every optimization algorithm, we have iterations. So for each and every thing, you need a loop variable, right? While you write a code, you need a loop variable. So xjki is the jth variable of the kth candidate. Means candidate is nothing but your student. So student is represented as k. Jth variable is nothing but j is nothing but your subject during the ith iteration. Right? Kth student, jth subject, ith iteration. So first index represents your subject, right? Second index represents your student. Third indicates your iterations. Okay, that's why it is represented in 3 different index, right? Then if you have a solutions, like you know, we call it a old solution, and by taking the old solution, we are getting the new solution. Like xn is known to you, you want to find xn plus 1. Once xn plus 1 is known to you, you will go for, by taking xn plus 1, you will take xn plus 2. Okay. So these are your old solution and this is your new solution. And once you get new solution, what you are doing? You are calculating f of x value. Similarly, there is a old f of x and there is a new f of x, right? So if old f of x is better, so you will keep as it is. But if new f of x is better, then you have to replace it with the old f of x value. The same thing applicable here. Now you can see the new value is represented by this dash symbol. You can see there is a dash symbol here. This represents we want a new value. So how to determine this value? X dash j k I. It is nothing but the old value. Okay, that is x j k I. R indicates your random number. So this is a random number. This is also a random number, a random number, random number, and this is also a random number. Earlier, if you see in the Jaya algorithm, what we are doing, we are finding the difference between best and current and worst and current. But now we are doing best minus worst. Right here you can see best minus worst solution. You are subtracting best and worst. Right. Your current solution is here. Right. And best and worst you have to identify and subtract it. Right. That is nothing but your Ravan algorithm, which is very simple. I'll show you the implementation. Now what you will do, if you go for second algorithm, in second algorithm you can see this particular part is same only, right? This is equation 1 only. And if you go to the third variant of Rao algorithm, this part is also same. Only thing is that you can see there is a modulus function here, right? Mod function here, right? That is the only difference. But equation 1 is also used in equation 2 and 3 respectively. Now you have a random number. This is a random number. What we are doing here, like if you remember TLBO second phase, that is learning phase. So each and every student need to interact with another student of his own choice. Okay. So like if I take student 1, student 2, 3, 4, 5, 1 is let's say pair with 2. 2 is let's say pair with 3. 3 is paired with 5. 4 is paired with 3. 5 is paired with 2. Right? Like that they are doing pairing. So here also we are doing the same thing. So here K is what? K is nothing but a student. L is what? L is also a student. So we'll compare the performance of K and L. If K performance is better, this particular term, okay, we'll write X, J, K, I. It is written OR, right? OR means first you have to check the performance of kth student with performance of lth student. Right? If performance of k student is better, the first term is xj ki and the second term is your xj li. Right? But if L is better in comparison to KL, if L is better, the first term you will take L, second term you will take K. In a similar fashion, when you go for Rao 3 algorithm also, K performance is compared with L, right? And if this is better, then what we are going to do? We are going to take XJKI. Okay, if Kth performance is better, okay? If Kth performance better, this part is XJKI and this part is your XJLI, right? If L performance is better than K, then this term you will write XJLI and this term you will take XJKI. Okay, like that, three different functions, okay, are there in three different variants of algorithm. Okay, but you can see here only the modulus function is changing. Here you can see there is no modulus, right? Here you can see there is no mod function, right? But here there is a mod function, right? Mod function means if some value is negative, we want to make it positive, so that we can get closer to the success. That is the reason the modulus is given, so that one solution will improve its value. That is the reason it is given, right? So as we discussed, again you can see here, what is xj best type? We have taken two value, one is best, another is worst. Best is representing the best solution. So xj best type indicates that the for variable j means for subject j. Okay, variable means subject you assume, right? For subject j, for the best candidate, who is best in a subject j. If worst I am taking, in that particular subject, you have to find the worst candidate. And as you are using the third index as I represents in first iteration. Second I value is 2 means second iteration. I value is 3 means third iteration. So in each and every iteration, you have to determine for a particular variable who is the best candidate who is the worst candidate. Right? Now, x dash jki is the updated value of x jki. I told you this is your old value, and this dash part is called as your new value. And these two random number are two random number of jth variable during ith iteration in the range of 0 to 1. Always remember, random number is taken in the range of 0 to 1. In MATLAB also we have seen we are writing a function array to generate the value in the range of 0 to 1. If you want integer, then you can say random integer. Okay, but here you have to specify more parameter. You have to specify integer minimum, integer maximum. Okay, and you have to specify the dimension, right? Number of rows, let's say, and number of columns. You have to specify these four values. Then you will get a matrix. Right? Now, in equation 2, 3, what you have seen? In equation 2, 3, you have seen xjki and xjli. I told you k is one candidate, L is one indicate. So these are the candidates. Okay, candidate solution k. Candidate solution, it is for the student k. This is the solution for student L. So candidate solution k is compared with any randomly picked candidate solution L. Like TLBO in the learning algorithm, we are doing pairing. Here also we are doing pairing. We are comparing K with L, where L is randomly picked from the solution set, right? And the information is exchanged based on their fitness value. And if the fitness value of Kth solution is better, out of if you check the f of x value for Kth candidate and Lth candidate, like student case, if a report card is issued to each and every student, by looking into the report card of kth student, Lth student, you can determine which student has secured good mark, right? If you see that the kth solution is better, then the fitness value of Lth solution, then this term, the first term is reduced to this one. We have written or, right? So those out of these two, whoever is the best solution, we have to keep that one in the first term. Worst candidate, we have to put in the second term. On the other hand, if the fitness value of Lth solution means this one, second one is suppose better, then the fitness value of kth solution, then this term you will do as xli. You are giving this part. Here you are giving this particular part. So we have to check the performance. Whoever is performing better, that is going to be considered here, right? Similarly, if the fitness value of kth solution is better in the second term, then the fitness of value of L solution, then this term is reduced to xjki. As you can see, if you go back to the equation, you can see both part we have written the same thing, xjki, xjli. Xjki is here, xjli is here. You choose this one, then you have to choose this one, right? If you choose this one, you have to choose this one. Similar fashion, if you choose here, you choose this one here. Otherwise, you choose here, you will choose here this one. Okay, how to choose this one? Based upon their fitness value, right? Okay, so if the fitness value of Lth solution is better than the kth solution, this particular term we are writing as xjli. So in this way, actually, this particular algorithm works, right? Now, even if you have not understood till now, you can understood this the term by the help of this example, because these are mathematical calculations. Now we will go for numerical one. So in the numerics, you can easily understand how these algorithms works. So let us concentrate this demonstration. Here we consider a on-constraint benchmark function of sphere. That function name is f of xi is equal to sum of I is equal to 1 to n xi square. Or you can write like this, x1 square plus x2 square up to it is xn square, right? And this is our f of x. As an objective function, we know either we have to minimize it or we have to maximize it. That's why here we have mentioned that we have to minimize it. Like previous lecture also, we have talked about Himagulav function, right? That is also you want to minimize. So you have to find out the value of xi that minimizes the value of the sphere function. And also a boundary is given to you, right? If xi is given to you, then there is a specific boundary is given to you. What is the boundary? It is in the range of -100 to +100. Okay. So you have to put a set of values here in order to minimize this particular function, and okay, in the range of -100 to 100. So you know, -100 square is same as +100 square, right? So in which case you will get minimum value? Can anybody guess? Put xi value in this particular equation such that the value is minimum. Which for which value you will get the minimum one? Can anybody guess? Or can anybody write in the chat box? Just guess it. If the range is given as -100 to +100 and the function is xi square, right? For which value you will get minimum value? Which value of x you will get f of x is the minimum one. See, if you take a negative number, we are taking square. So the negative number will turn to a positive number. Yes, madam has also already mentioned, Savita Vansal madam, that values are 0, obviously. Because if you take negative value, its square is positive. If you take positive value, its square means it will come a big value. Only if you take the value as 0, 0 square is 0, right? So for the 0 value, you will get the minimum f of x. So the known solution for this benchmark function is 0 for all xi values of 0. So sometimes a problem is given to you for which you know what is the solution, but getting that solution is not feasible, right? Like I told you, a very large state space if you take, like I gave example of 512 task and 16 different machine. So in that case, we are getting 16 to the power 512. It is difficult to go through each and every possible solution, right? But if you know the known value is 0, then you know the value should come close to 0. Otherwise, you are not closer to the global solution, right? So let us see how we can proceed using Rao-1 algorithm. Okay, so like TLBO and Jaya algorithm, here also we consider the population size. What is population size? That is called as your candidate solution. In simple term, you can say number of student in your class. So number of student in your class, we have assumed as 5. And we have considered the number of design variables. Number of design variable is same as number of subjects the students are studying. So that is 2. We consider that is x1 and x2. And every optimization algorithm is having a termination condition. Last class we have considered the termination condition as only one iteration, but here we will go for 2 iteration, right? As it is a minimization function, obviously the lowest f of x is better. So what you will do, you have 5 different students, you have 2 different subjects, you have to generate the initial population, and initial population is in the range of, we know that is in the range of -100 to +100. If there are 2 variables, both values need to be 0. If there are 3 variables, Savita Bansal madam tried it in 0, 0, 0. That means there are 3 different variables. You can assume n number of variables, right? In this example, we are taking 2. Madam has taken an example of 3, right? Like that, you can say that what are the values of x1, x2, and x3 in order to determine f of x. Now, if you generate these values randomly, these values are completely random. So I have taken this as randomly. So first value it is coming is x1 is equal to -5, x2 is equal to 18. So how to get f of x? F of x is nothing but -5 whole square plus 18 whole square. Can anybody calculate and tell me what is the value we are getting? Minus 5 whole square is what? It is 25, right? 18 whole square is 324. Okay, if you calculate the sum, you will get the value as 349. Okay, that is your f of x value. Okay, similarly, for the second student, what you will do? You will calculate 14 square plus 33 square. You will get 1285. 30 square plus minus 6 whole square. You will get 936. Minus 8 whole square plus 7 square. You will get 113. Minus 12 square plus minus 18 square. You will get 468. Okay, now you got f of x value for all the 5 different candidates or students. So what we will do? Out of these 5, as it is a minimization problem. Yeah, there is a question. What is the difference between TLBO and drive? TLBO algorithm, sir, we have two different phases, right? Teaching and learning. Here there is only single page. That is the primary difference. Okay. Teaching learning phase, there is a, in the teaching phase, if you see, there is a teacher, there are number of students. There is no concept of that thing here. Here we are looking for best and worst solution. Again, your next question may be, what is the difference between Joya and Rao algorithm? Joya algorithm has only one page. Their best and worst solution is compared with your current solution. Okay, if you see Joya algorithm, okay, you can open my PPT, you can see it is checking with the best and current solution, and it is also checking with worst and current solution. But Rao algorithm, we are not doing this one. Now one algorithm we directly take best minus worst solution, right? So this is the primary difference between TLBO Rao and Joya and Rao algorithm. Okay, so out of these f of x value, which value is minimum? Because it is a minimization problem, you have to find the minimum value in this particular column. So minimum value in this particular column is 113. Right, minimum value is 113. So it is called as your best solution. Maximum value is your worst solution. So I am considering this one is my worst solution. The same thing, whatever we discussed till now, the same thing is done by your Joya algorithm. Only the formula is changed. That is the only difference. Okay, so let us proceed. Now, in order to get a new x1, new x2, you know old x1 and x2. Our objective is to find new x1, new x2. Once you get new x1 and x2, by using these two new value, what you will do? You will calculate f of x new. Okay, let's say I am writing new f of x we are finding. Right, first you calculate new x1, new x2. Simply put in the x equation, you will get your new f of x. Then we will compare with this old f of x. Whichever is better, we will retain it. Whichever is not better, we will discard it. Okay. How to get new x1? I'll take the old x1. I'll take the base solution. I'll take the worst solution. Okay. And along with that, we need also random number. You can, if you look into the equation, this is the actual equation. You can see this is the equation. What you need in order to calculate the new solution, this is your old solution, this is random number, this is best minus worst. So if you calculate this one, what is old solution? Old solution is minus 5 or not? See here, this is minus 5 plus random number is, we assumed it is 0.10. It may be any value in between 0 and 1, but you have to generate, right? Some value will come, you have to consider that one. What is best one? Best one is minus 8. What is worst one? Worst one is 14. So this will give you new x1. Okay. So solve it, you will get minus 7.2. Right. Now, if you calculate new x2, so let me write in another color so that you can consider. New x2 means you will take your current solution. Sorry. Okay. Current solution, worst solution, and best solution. Okay, this is for x1, this is for x2, right? So I can write 18 is my current solution plus x2 random number. Okay, that is 0.50. Then best is 7, worst is 33. So if you solve it, you will get the value as 5. So we got new x1 and new x2. What is our next step? We will calculate f of x with these new values. So which is nothing but minus 7.2 whole square plus 5 whole square. Can anybody calculate and tell me what is the value we are going to get? Minus 7.2 whole square. Let me do also with you. 7.2 multiplied by 7.2. I hope you will get 51.84 plus 5 square we know that is 25. If you add 25, we will get the value is 76.84. Check once whether you are getting the same value or not. Write in the chat box. Are you getting 76.84? Yeah, Nicholas sir mentioned he is getting. Okay. So what is our current f of x value? Means old f of x value. Old f of x value is 349. New f of x value we got 76.84. Which one is better? It is a minimization problem. So new is better or old is better? It is a minimization problem. Which one is better? Guess it, old or new, by looking into these two values. New is better, right? New value is less in comparison to the old value. So what we will do, we will keep these two value, x1 and x2 value, new x1, new x2 value, add this f of x value, and we will delete these values. Right? One more you try. If I show you another one, okay, you calculate for second one. So I'll take, let me erase. Okay, if I calculate for the second candidate, so I'll take second candidate and the best candidate, and here worst candidate is same as your second candidate. So in order to find the new x1, you will take your solution, that is 14, right, plus random number is 0.10. Okay, and best minus worst. Best is minus 8, worst is 14. Similarly, if you find new of x2, okay, let me use another color, right? So it is nothing but 33 plus random number is 0.50 and best minus worst. Best is what? 7. Worst is our 33. Okay. So if you solve it, how much you are getting? So let me calculate once. Minus 8 minus 14. So minus 22 multiplied by 0.10. You are getting minus 2.2 plus 14. So you will get the value is 11.8. Similarly, 7 minus 33. So it is 26 minus 26 multiplied by 0.5 means minus 13 plus 33. So you will get 20. Okay. So in order to calculate f of x, what you will do? You will write 11.8 whole square plus 20 whole square. So 11.8 into 11.8, it is 139.24, and this you know it is 400. So you will get the value as 539.2. Now, if you compare with your old f of x value, this is your old value, right? And this one is new value. Which one is better? Which one is better? Obviously, new one is better because it is a minimization problem. This value is less. So we will retain these values and we are going to discard these three values. Like that, if you do, these are the new values, okay, and these are the old values. So what you will do? Now you can see already I told you we'll keep new value for these two. Come to the third one. Third one, you are getting 936 as your old f of x and 1133 as your new f of x. So what you will do? You have to discard the new solution. You have to accept the old solution. Next case, it is 113 here, it is 140 here. So again, you will keep your old solution, you will remove your new solution. Last case, it is 468 here, it is 1162 here. So you have to keep the old solution, discard the new solution. Right? In this way, now if you go for the new sample, you will find the first two populations are new, these are new. And the rest population is old. Now, which one is the best? Before starting of this iteration, which one is best? 130. Now we see which one is best. You can see the best one is 76.84. So the best value is improved from 113 to 76.84 after end of first iteration. That is not only the job here. Your job is, you can see here, which one is the worst solution here. Worst solution is 1285. But if you look into the worst solution here, it is 936. You have not only improved the base solution, but also you have improved the worst solution. Okay, the worst value of the objective function is improved and the best value is also improved. Okay, so in this way, you can see this is not only the one iteration, this is one iteration, but you can go for 20 iterations, 40 iterations. Okay, like that, if you see, the value will be close to 0. Here the value is 76.84, which is very away from 0, right? But when you do it for multiple iteration, you will see the value will be close to 0. Okay, so see here. Now, what is our termination condition? The termination condition, I told you, there are 2 steps you have to do. 2 iterations you have to do. We have completed only 1 iteration. So we'll proceed for the second iteration. Okay, what we will do in the second iteration? In this case, in the previous case, if you see, the best one is your student number 4. Worst one is your student number 2. Now, this is in I is equal to 1 case. When you take I is equal to 2 case, the best is your candidate 1, worst is your candidate number candidate 3. Right? Every iteration you will get a different one. Okay. Now, in order to get a new x1, x2 value for candidate 1, let us try how to get a new x1. For new x1, which one you require? You require the current value, that is also the best value. And you have to also take the worst value. So I can write minus 7.2, which is my current value, plus one random number. Let's say the random number is 0.8 here. Then best minus worst. Best means minus 7.2 minus 30. Right? Similarly, if you calculate the new x2 value, which is nothing but you can say x2 value, right? This one. X2 value means you will take these two. So 5 plus second random number, that is 0.1. Best minus worst means 5 minus 6. So you will get a new x1 value. I have already calculated here. That's why I'm directly taking this value, but try to calculate and verify with these answers. Right? Sometimes I may also commit mistake, right? So the new x1 value is minus 36.96 and a new x2 value is 6.1. So if you calculate new f of x, then what is the value? Minus 36.96 whole square plus 6.1 whole square. Okay, so calculate it and tell me what is the value. 36.96 multiplied by 36.96. So you will get 1366 0.0416. Okay. Similarly, 6.1 multiplied by 6.1. So you will get 37.21 is 7. Okay. So if you add these two value, okay, how much you are getting? You are getting 1403.2516. Okay, 1403.2516. This is your new f of x. What is your old f of x value? Old f of x value is 76.84. Right, which one is better? Old f of x is better. So this new solution is discarded. Okay. Now, similarly, if you do, these are the new solution you are going to get and these are the old solution. First case, I already told you, old solution is better, new solution is not better. Second one, you are getting old f of x, you know that is 539.24, but new case, you are getting 767. So obviously, old is better. Discard the new one. But third case, you can see old f of x value is 936, but new f of x value is 24. Right? So you have to accept new f of x value and discard the old f of x value. Right? Fourth one, new is your 1491, old is your 113. So you will keep old one only, discard the new one. Last case also, you are going to accept the fifth one, you have to discard this one. So if you see this one, this example, right? 1, 2, 4, 5, we are taking from the old part, and only the third population is the new one, right? And if you remember, before iteration 1, the best fitness value we got 113. Okay. After the end of the first iteration, what is the best value we got? We got the best value is 76.84. Similarly, take the worst value also. Not only best is important, worst is also important, right? So worst value is 1285 and it is improved to, after end of the first iteration, it is improved to 11, I think, sorry, it is improved to 936, okay. 9, 3 and 6. Okay, this is after first iteration. After second iteration, which one is the best value? Best value is 24.0676. Worst value is 539.2. Okay. Best value is 24.0676 and worst value is 539.2. You can see gradually the value is decreasing. Okay. Not only the best value is decreasing, but also the worst value is decreasing. You are improving your solution by looking to the best solution as well as the worst solution. Okay. So this is the result after the end of the second iteration. Do number of iterations after 20 or 30 or 50, you will see the value will come close to 0. Okay, if we increase the number of iteration, then the known value of the objective function is our 0. We know for this unconstrained benchmark function of sphere, the well-known solution is 0. Right? So we will take these to 0. But instead of minimization problem, it is a maximization problem. Then what will happen? Instead of checking the instead of taking the small value, you are going to take the large value. Okay, you are taking your minimum value, right? But you can take the maximum value in that particular case. If any doubt, you can ask. This is about the Rao-1 algorithm. Any question related to Rao-1 algorithm? Okay, if you understood this algorithm, let me proceed to the Rao-2 algorithm. Okay. Okay, we'll complete the theoretical part. Then I'll show you the demonstration of Rao-1 algorithm. Okay, there is a question. How we can achieve the exploration and exploitation here? Okay, exploration says that global search, right? Exploitation says that local search. Both you want to achieve. We are considering, you can say, the best value. You are close to the best value where you are doing the global search. At the same time, you are avoiding the worst part. That will be your exploitation part. Right? Both you are handling in a single equation. In that way, you can see this algorithm works. Not exactly we are doing that one, but somehow it is related to that only. Okay, so let us see about the second variant of route to algorithm. Only you can see in this case the difference you will find in the form of that function, right? Rest things are same. So here we consider actually the population size is also 5. That means in your class you have 5 students. They are studying two different subjects, which is we call as decision variable, that is x1 and x2. Here also we can consider the termination criteria is there is two different iterations, right? So now, you know, once you generate this population, right? This population, then you can calculate f of x. F of x is nothing but x1 square plus x2 square. Okay, if there are more variables, you take x1 square, x2 square, x3 square, so on up to xn square. Okay, and the best one is your candidate number 4 because it holds the minimum value. Worst one is the candidate number 2, which is the best one. This is the worst one, right? Okay, now what we have to do, we have to find new x1 and x2. But here the formula is a little bit different in comparison to RAW1 and RAW2 algorithm. Okay, see how it is different. So this is the formula. So let us take the first candidate. Okay, so for first candidate, x1 value is -5. Okay, best value is -8, worst value is 14. Using these values, what we will do, will complete the first part. So let us see how we'll do. So I'll take current value, that is -5, plus random number is 0.1. Then best minus worst, which we already done in RAW1 algorithm, that is -8 minus 14. Okay, first part is done. Now, if you go for the second part you need one random number, right? The random number is 0.5, we have considered here. But here you have to do one competition, right? So you have to pair the first candidate with another candidate. You can pair it randomly. So for example, I can say first candidate has interacted with the second candidate. Any candidate you can interact to, and that is purely based upon the outcome of your random number, right? Suppose while generating the random number, you got first candidate is having pair with the second candidate. Okay, so if you see the first candidate and second candidate, these two and their interaction, who is better? Obviously, the first candidate is better. Second, because first candidate fitness value is 349 and second candidate fitness value is 1285. The first candidate is only better. So what we will do, I told you, if you remember, I told you x j k I, x j l I. So here k indicates your first candidate, L indicates your second candidate. If the fitness value of xjki is better, like in this particular case, first term you are going to take is k. K means first term is your -5. But as a formula, you have to take modulus here, right? And the next term is the opponent. Your opponent is L, that is the second candidate. The second candidate value is 14. That also placed in the modulus. So if you solve it, it is -11.7. Right? Now, if you go for the second variable it is 18 for the current solution, 33 is for the worst one, 7 is for the best one. So it is 18 plus another two random number I have taken 0.60 here. Okay, 0.6. Best minus worst. 7 minus 33 plus. Okay, the second random number is 0.2. Then out of these already we know first one is the better than the second one. So what we can do? We can say 18 modulus minus 33 modulus. So first value you will get the value is minus 11.7. Second case you will get the value is minus 0.6. Okay. So what is the guarantee again whether this value is better or not? Again you have to calculate f of x value, which we call as new f of x. So new f of x is nothing but minus 11.7 square plus minus 0.6 square, which is equal to, see here, can anybody calculate and tell me? 11.7 into 11.7. What you are getting? It is 136.89 plus 0.6 into 0.6, 0.36, right? Sorry, yes, 0.36. So if you add with 136.89, so you will get the value is 137.25. Okay, now you tell me whether your old f of x better or new f of x is better. Can anybody answer? Old f of x or new f of x? New is better, right? So you have to keep these values of x, new x1, new x2, and a new f of x. Discard the old one. Right? You have to discard the old one. Right? Now you have done the interaction with 1 and 2. You have to do interaction of 2 with someone, 3 with someone, 4 with someone, and 5 with someone. Let's say interaction happens between 2 and 5. Interaction happens between 3 and 1, 4 and 2, and 5 and 4. Okay. Now if you compare, right, new f of x already we have compared for the first candidate, but you have to compare for other candidate. First candidate case we have seen the new value is better, old value is not better. Okay, come to second one. Second one case we got what 1285 here, 324 here. So 324 is better. 936 and 602. 602 is better. The third candidate also the new one is better. Fourth candidate case, the old one is better. Fifth candidate case also old one is better. So first three case new value is better. Next two case old is better. So come back to this. Come to this slide. So here you can see these are your new solutions, which is performing better than the old solution. But for the last two candidates, old solutions are better. And before this iteration, if you see which one is your best value, best f of x value, best f of x value, if you calculate, it is coming 113. Worst is coming as 1285. And now check which one is best. Best is again 113. It is not degrading, but it is same. But worst is improved to 602.73. So sometimes in two consecutive iteration, you may not get a difference. You may get the same value. That's why we are doing for couple of iterations. After the couple of iteration, you will see the value will be close to 0. So this actually completes our one step of our two algorithm. But what is the termination condition we have considered here? We consider the termination condition is two different iterations. Okay, you have to do two different iterations. First iteration is done. So second iteration, what you will do with this new population, again you have to do, right? So for example, I'll take here the best one is your candidate number 4. Worst one is candidate number 3. and you have to take the current one is 1 and paired one also you have to take, right? So 1, 2, 3, 4, 5. For all, candidate 4 is better. Candidate 3 is the worst one. Only pairing may be different. So here we suggest this type of this pairing based upon our random value, that is 1 and 4, 2 and 3, 3 and 5, 4 with 2 and 5 with 1. Okay, now let us see how to get new x1 value. So I am taking this value is your current value, is your worst value, and this is your best value. In order to calculate new x1 value, okay, you will get minus 11.7 plus first random number is 0.01, best minus worst, best is minus 8, worst is minus 15.3, plus second random number is 0.1, right? Now you have to compare with your paired one. Now 1 is paired with 4. 1 is paired with 4. You tell me, if 1 is paired with 4, which one is providing the best solution? If you 1 and 4, they will compete each other. Who is the winner? The winner is 4, because its f of x value is minimum. As its f of x value is minimum, it is better one, right? So first you will write the best value. Best value is 8 and 8 modulus, and next you will write worst value. Worst value is minus 11.7 modulus. So you can calculate this one, you will get new x1. New x1 you will get is minus 12.303. If you solve it, you will get minus 12.303. Now if you go for new x2 is nothing but, you will consider these 3, right? So minus 0.6 plus first random number is I have taken 0.1. Okay. Then best minus worst means 7 minus of 19.2 plus second random number is 0.5. Then out of 1, 4, who is better? 4 is better. So I am taking 7 modulus. Okay, 7 modulus. Then I'll take minus of minus 0.6 modulus. So if you solve it, you will get the value is 5.2, which I have given here. Now, if you calculate your new f of x, so it is nothing but minus 12.303 whole square plus 5.22 whole square. Okay, calculate it and tell me what is the value we are getting. 12.303 multiplied with 12.303. I hope you will get 151.363809. Similarly, 5.22 multiplied by 5.22 will get 27.2484. If you add these two, you will get the value is 178.612209. Okay. So see here. So we got 178.612, right? You can see here. But which one is better? 178.612 is your new. This is your new f of x. This one is your old f of x. So if you compare, then you will get your old f of x is better. Similarly, after interaction of the second with the third, where fourth is your best one and third is your worst one, you will get the new f of x is 316. And if you compare with the 324, your new solution is better. Okay, old one is not better. Coming to third one is interacting with whom? Third is interacting with fifth one. Again, best is 4 and worst is 3. If you calculate it, you will get the new f of x value is 512.331, but old f of x value is 602.73. So obviously your new value is better, so you have to discard the old value. Similarly, fourth is interacted with whom? Fourth interacted with 2. Okay, and best is 4, worst is 3. If you take, then you will see the best one you are getting, the best value you are getting the new f of x. Worst one is your this is your worst one. Okay, slightly it is improved, right, in the new f of x value. In the similar fashion, if you take this one, this is 468 for the fifth one. After interaction with the 1, fifth is interacting with 1. So you will see here that your old f of x value is 468, but new f of x value is 730. So old one is better, new one is not better. So you can see first and last case, new is better. Sorry, first and last case, old is better, and rest of the cases, new is better. So this is your updated population. First and last, old is better. These three are new population. Now compare with the performance. If you see, the base solution we got is 113 before first iteration. Now it is improved to 107.517. Not only that, worst case if you see, it is 18285 earlier, but now it is improved to 512.331. Right? Like that, if you continue a set of iteration, you will get the value close to 0. Okay. And instead of minimization function, if you take here as a maximization function, so the best value means the maximum value. Like you are taking here the minimum value is the better, right? If you go for a maximization problem, you will take the maximum value. In your respective research area, you can see that whether you want to minimize or you want to maximize. Based upon that, you can take a decision. Yeah, any question related to route to algorithm you can ask. Okay, if it is clear to you, let me proceed to RAW3 algorithm. Okay, so here also we consider the number of students as 5, which is our population size, or we can say candidate solution. And number of subjects or design variables x1 and x2. Okay, so there are two, right? We have considered 2. And termination conditions is same like previous 2 algorithm, that is RAW1, RAW2 algorithm. Termination condition is after 2 iteration. So it is a minimization function. We have to choose the lowest value is better. What you will do first is there are 5 student and 2 different subject. You will generate the initial population. Okay, and respectively you will calculate the f of x value, which is nothing but x1 square plus x2 square. Okay, so that you will get this f of x value. After that, you have to find the minimum f of x. Minimum f of x you are finding in the candidate number 4. So you declare fourth candidate is the best candidate. And you can see here the second candidate case, you are getting the worst result, right? Or you can say maximum f of x. So you declare the second candidate is your worst candidate, right? Now, in order to get new x1 and x2 value, you will use the RAW3 algorithm formula, right? So here also interaction is there, like previous case interaction is there, here also interaction is there. But the difference you will find is that in terms of the modulus function, right? So for x1, or if you go for candidate 1, x1 is -5. Which x1 is better? -8 is better. Which one is worst? 14. Right? Now, with these values, you can update x1. right? And assume that candidate 1 is interacting with candidate 2. That's why it says that for the first candidate, new values of x1, x2 during the first iteration is calculated as follows. That is, here the first candidate is interacting with whom? The second candidate. Like previous case also, we do it the same. If the fitness value of the first candidate is better, so in the first term you will write first candidate solution, right? So the information exchange is from one first candidate to the second time, otherwise second candidate to the first candidate. Okay, so if I calculate here for the new x1, x2 value, how will calculate new x1 value? First we will take old value, that is -5. Random number is 0.10. Okay, best value is -8. Worst value you will write in modulus. So 14. Okay, plus second one you will get 0.50, second random number. Okay, now best value will put in modulus. Which one is best? If I take pair between 1 and 2, you know first solution is only better. So I'll write -5 minus, then worst solution I'll write, that is 14. This is nothing but the interaction of 1 and 2, 1 with 2. Right? This will give you new x1. Then let us go for new x2. New x2 can be determined using these three value. That is 18, okay, plus 0.50, best is 7, minus worst is 33. Okay, plus what you will do? Next, sorry, yes, the random number is not 0.5, it is 0.6. Okay, this random number you put it. Okay, plus second random number we are taking 0.2, and the best value out of 1 and 2 is here 1 only. So I am taking 18 modulus minus 33, which is nothing but x2 value, the worst one, right? So if you calculate this one, in fact I have calculated in the next slide. So you can see the value you are getting here is minus 11.7. Here you got the value is minus 0.6. Okay, so if you calculate new f of x, it is nothing but minus 11.7 whole square plus minus 0.6 whole square. Okay, can anybody calculate and tell me what is the value? So 11.7 multiplied by 11.7. So I'm getting 136.89. Then 0.6 into 0.6, you will get 0.36, right? So you will get 137.25, right? So this is your new f of x, and these values are your old f of x. So if you compare new f of x with the old f of x value, you will see your new f of x value is better, old f of x value is not better. Right? So see here, if you compare your old value with the new value, so new f of x value is better, old f of x value is not better. Similarly, here we consider the same interaction, 2 with 5, 1 is interacted with 2, 2 is interacted with 5, 3 with 1, 4 with 2, and 5 with 4. So if you compare 1285, which is nothing but the fitness value of candidate 2, old value, and 324 is the new value. So 324 is better. This one is not better. 936 and 516.33, which one is better? New value is better. But last two case, you can see 113 and 364 means 113 is better. 468, 835 means the fifth population is better. Okay. Now, if you see updated population case, First three candidate case, we accepted the new solution. Okay, you can see these three candidate case, we have considered the new solutions. Okay, updated solutions because their value is better in comparison to the old one. But if you see for candidate number 4 and candidate number 5, the new solution is not better. So we took the old solution, right? So here also, like previous algorithm, route 2 algorithm, the best population before iteration 1 is 4 only. After iteration 1 also, the best population is 4 only. That means the best value is not improved after iteration 1. But if you compare to worst value is earlier 1 to 85. Now it is improved to 516.33. It is a good improvement. Okay, worst value is improved, but best value is not improved after the first iteration. But what is the termination condition? The termination condition we have considered here is that the number of iterations should be equal to 2. So we'll proceed for another iteration. So if you go for second iteration, I have to take current value, best value is your fourth population, and worst value is your third population. So if you calculate, minus 11.7 is your old value in order to find the new x1 value. Minus 11.7, first random number is 0.01. Okay, and best minus worst means minus 8 minus modulus of 15.3. Worst case you will put modulus. Second random number if you take, it is 0.10. Okay, 0.10. Okay, second random number is this one because it is for x2, right? Oh, no, this is for x1 only. So this one, 0.10. Then interaction is required. Suppose I am taking interaction between 1 and 4. Compare the fitness value of 1 with the fitness value of 4. So 4 is better. So I have to keep the first term is the fourth population's x1 value in modulus minus of first population x1 value, which is minus of 11.7. Okay, so if you solve it, you will get the value is minus 9.963. Similarly, if you calculate using these values, okay, it is minus 0. That will give you new x2 value, that is minus 0.6 plus, I'll take this 0.10. Okay, then best minus worst, that is 7 minus modulus of worst, you should put in modulus 16.8 plus interaction of 1 and 4. I'm taking second random number, that is 0.5. Okay, so out of these the best is 7, that you will put in modulus, minus of worst is minus 0.6. So if you calculate this one, you will get 2.22. Now you got new x1 value, you got also new x2 value, right? So if you compare new x1 value with the new x2 value, okay, sorry, new x1, new x2 value you got. So if you calculate the f of x value, which we call as new f of x value, it is minus 9.963 whole square plus 2.22 whole square. So calculate this one. Can anybody calculate what is the new f of x you are getting? So you will get minus 9.963 whole square. It is 99.261369 plus 2.22 into 2.22. 2.22 into 2.22. How much you will get? You will get 4.9284. If you sum these two, It is 104.189769. Okay, this is the value you are going to get. So if you compare new f of x value with old f of x, obviously new f of x is better. So new f of solution you have to retain, old f of solution you have to discard. Is not only the interaction, you have to do interaction with 2 with 3, 3 with 5, 4 with 2, and 5 with 1. So after this interaction, you can see you will get these are the new f of x value and this is the old f of x value. So first one we have compared, we know 103, 137 and 104.189. 104.189 is better. Now, if you go for the second one, 324 is the your old f of x, new f of x is 944. So old is better, new is not better. 516.33 for candidate number 3, right? And new f of x value is 217, right? So obviously the new f of x is better, old f of x is not better. If you go to candidate number 4, the old f of x value is 113, right? And new f of x value is 77. Obviously, although it is a base solution, you can get better result than the base solution in your new x1 and x2 value, right? That is new f of x value. Okay. The last one, the candidate number 5 case, if you compare old f of x with new f of x value, your new f of x value is better, right? So except I think old f of x is better for the candidate solution 2, and rest of the cases the new solution is better. So if you look into the updated solution, okay, you can see here these all are the new solutions: candidate 1, candidate 3, candidate 4, candidate 5 case you are getting new solution is better, but only in the candidate 2 case you getting old value is better, right? And if you see our base f of x value before iteration 1 we got it is 113, right? But now it is improved to 77.853. And similarly, if you go for worst one, worst is earlier it is 1285, but after this second iteration, we got the worst value is 324. So not only we have improved the base solution, but also we have improved the worst solution. So if we increase the number of iteration, then you will see the value is will get close to 0 after a couple of iterations, right? So in this way, you can solve the problem of Rao 3 algorithm, right? If you have any questions, you can ask. Any question? Okay.
Hello.
Yeah, yes, sir, please.
Yes, sir. Sir, thank you very much for the excellent lecture you're providing us on RAW algorithm. But sir, I mean,
Yeah.
what is the practical part? I mean, I'm asking about the algorithm on MATLAB or on Python. I mean, how we should
No,
run it.
you can implement in any programming language, but I'll show you the implementation part in MATLAB. I'll
Okay, sir.
implement
Okay,
Rao
sir.
one algorithm now.
Okay, sir. Thank you very much, sir.
Yeah. Okay. So you can implement any algorithm, but I'll show you the demo for Rao one algorithm. Okay. So let me open MATLAB, and I request all of you to open the MATLAB. I'll go back to Rao one algorithm. So please open MATLAB. Once you have once you open MATLAB, then you can work with me. So it will take some time to open the MATLAB. In between, if you have any question, you can ask. Yeah, now it is open. So what we have to do, we have to open a new script. Okay, and save this one as your raw1 algorithm. Let me save in my desktop. Okay, so let us start with the implementation part. So you can use the command clc clear to clear all the variables from the workspace. Now there is no variable in the workspace, but even if there is a something there in your workspace or in command window, in order to clear that, we are writing clc or clear. Right? If you want to print some kind of message, you can write disp, that is display. Suppose I want to write a comment here that implementation of raw1 algorithm. So this message will be displayed in the command window, right? Okay. Now, in previous implementations also, I told you number of students we have considered as 5 and number of subjects we have considered as 2. So these are static declaration. At any point of time, you can change based upon your research domain or based upon your application, you can change. And in the first implementation, I told you, if you remember, we have taken a constrained benchmark function of sphere. There we have specified the range of the variable is in between -100 to +100. Okay, so I am writing that as a lower limit is my -100 and upper limit is +100, right? Okay, so we'll start with the first iteration. That's why I'm taking a variable that is iteration is equal to 1, and my number of iterations I'm considering as, let's say, 2. Later point of time you can change it as per your requirement, right? And if I also need the random number in order to get the same result. So the random number considered here is 0.10 and 0.50. So let me write in my code random number we want to take here is 0.10 and 0.50, and another set of random number we have used for the second iteration. Let me check what is the random number. Yes, 0.80 and 0.10, right? That I want to write here. Let me write here 0.80 and 0.10. Right, this is the only static things you have to do, or you have to assign these values. At the point of time, if you need, you can change the lines, whatever you have written within these two complete line as for your requirements, right? But don't use these student as 5 2 in your code. When you change in one location, then it is not showing you correct output, right? But if you change here, then it will show you correct output because you need not change in each and every place. Now we know how to generate the population. So here we have population. I have to copy that population. You can generate the population, or you can take population directly by writing population is equal to, in square bracket you have to mention -5, 18 is the first row, then 14 and 33 in the second row, 30 and minus 6 in the third row, and minus 8 and 7 in the fourth row, and minus 12 and minus 18 in the fifth row, right? Or you can write, you can generate this population by writing two different for loop. Now, how to check the fitness? You know, if I calculate, if I do minus 5 square and 18 square, I will get the fitness value of my first population. So let me write a simple for loop. I'll write for I is equal to 1 to students, right? I is equal to 1 to students, right? Then I also need the two-dimensional these values, right? For each student, you have to calculate fitness, but you need both x1 value and x2 value, right? So you can write fitness of I is equal to, that is fitness of the first student you are calculating first, then second student, third student, fourth student, and fifth student. So you can do by writing population of I comma 1, that is 1 comma 1, that indicates minus 5. Okay, when I is equal to 1, it is multiplied with the population of I comma 1. So that will give you the square, right? Similarly, I have to take population of I2. Is there any? Okay. I also need population of I comma 2, population of I comma 2 multiplied by population of I comma 2 again. And then I put a semicolon. Okay, this will give you the fitness value. Right, population is already mentioned here. This will give you the fitness value. Let me run and see is there any error or not. Oh, this is your. I have opened two MATLAB. Yeah, here you can see. I'll show you both window. Yeah, you can see in your output screen. Now you are getting a message implementation of Rao and algorithm. And in the workspace, you can see a set of variables that you have declared in your script. And if you open the fitness value, fitness, then you can check the values. Yeah, now you can check the fitness values in this one, which is 349, 1285, 936, 113, and 468. So if you go to my slide also, you can see these values you are getting, right? That is the first part is done. So what is the second part? Now I have to select which one is best, which one is worst, right? And this calculation I need for all the iterations. So I'm writing for I is equal to, or you take a loop variable k, because I is already there for the student, a up to number of iterations. So it should run for number of iterations. And I need to find who is the best candidate. So I'm assuming the best fitness is very large number. You take as many as large number as possible, because this number will never reached by any value. Like if you do 100 square, okay, plus 100 square, so you will get 1 followed by 4 zeros, right? 100 into 100, and the answer another 100 square means 1 followed by again 4 zeros, right? So the sum is actually 2 followed by 4 zeros. So you have to take a value bigger than that, right, for the best fitness value. Similarly, worst fitness is will take 0, because until unless you will take the best and worst fitness, it is difficult to find the best candidate and worst candidate. Now, in order to find the best fitness, I'm writing for I is equal to 1 to students. If the fitness value of the first one 9 is less than the best fitness. Best fitness will consider a big number, right? So obviously it is less. Then I can say best fitness is equal to fitness of I. Right? And I also need to write best fitness index. best fitness index is I, because later point of time I need that particular index while in order to extract the x1 value and x2 value. So this will give you the best candidate, right? Similarly, you can write another loop for the worst candidate. So I can write the same loop for I is equal to 1 to students. Then if the fitness of a particular candidate is greater than the worst fitness. So worst fitness we have assumed as 0 here, you can see, right? So if the value is greater than 0, then 349 means it is 349 is greater than 0. So it is going to come, right? So is equal to worst fitness. Then I can say worst fitness is equal to my fitness of I, right? Then I also need worst fitness index in order to extract the x1 and x2 value. So I got, okay, worst fitness index is I and best fitness index is I. So it will keep one index of the best candidate and this will keep the worst fitness index, right? Now, once you get worst and best fitness, what is our next job? Our next job is to calculate the new population. New population means new x1, new x2 value followed by new f of x. So for that, for I is equal to 1 to students. Okay, for j is equal to 1 to subjects. Okay. So we have to find new population of I comma j. Right? How to find new population of ij? You have to take your old population. Old population is there in population. So I'm writing population I comma j. Okay, plus random number. I have already mentioned these random numbers, right? So I need that random number. Otherwise, you can use rand function, right? But in order to get the same result which is given in my slide, so you have to use static declaration. And once you understand this one, you can remove it for your code. So random number iterations comma j. Okay. For the first iteration and for the first subject, it will take 0.10. Okay. Then it will take 0.50. When you go for the second iteration, it is going to take 0.80 followed by 0.10. Okay. So random number iteration j multiplied by, okay, then I have to take population, best population and worst population value. So I'm writing population best fitness index comma j minus population of worst fitness index, right? So worst fitness index comma j. This will give you best fitness and worst fitness. Okay. Now, if you go for new fitness, so for I is equal to, and now you calculate new fitness, then only you can compare with your old fitness value, right? So for I is equal to 1 to students, calculate the new fitness value, new fitness of I. Already you calculated the fitness, I think. You copy that one, just replace population with new population. That will solve your problem. Okay, you can say new population I comma 1, new population I comma 1, new population I comma 1, I comma 2 multiplied by new population I comma 2. Only have replaced population with new population, right? Okay, now new population also we have calculated. Okay, what is our next step? Our next step is to compare one with another, right? So for I is equal to 1 to students, I'll check the old fitness with new fitness. If new fitness of I New fitness, if it is larger than old fitness, then what you will do? You have to do nothing. No need to do anything. Right? Only if it is less than, then only you have to consider. So let me write the else part. The fitness of I is equal to new fitness. So I'm updating the fitness. Right? If fitness is better than new fitness. Right? In that case, new fitness is better. New x1, x2 is better. So not only that, you also need all the x1, x2 values, also new x1, x2 values. So subjects, right? Subjects. Population I comma j is equal to new population. You are overriding with old population. Okay. This will complete these steps. Then you can increase the iterations, right? As much you require. So I'm adding one because it will start the second iteration again. Okay. Now and end. Right. So let us see if I run for only one iteration. Let us first run for one iteration and check the result. If it is correct, then I'll show the rest of the result. Okay, it is showing some error. What is that error? The error says that iterations. Okay. Okay. Somewhere I have written iterations. Somewhere I have written iterations. That is the problem. Okay. Now it is successfully executed. So what I will do, I will check the fitness after the first iteration. Okay, that is 76.84, 539.24, 936, 113, and 468. So let me go to slide and check whether the same value we are getting or not. After the first iteration, yes, after first iteration, these are the values. Okay, so let me compare with these values, whether same value we are getting or not. Yes, we are getting the same value. 76.84, 539.24, 936, 113, and 468. Right? Now, if you go for one more round, we are expecting this value, right? What is that values? This value 76.84, 539.24, 24.067, 113. Let us see whether we are getting or not. If I take the number of iterations as 2. Okay, check. Let us check. Yeah, I'm getting 24.0676. Okay. So here you can see the result is improved from 113 to 24.0676, and worst fitness value is also increased from 1 to 85, right? 1 to 85 to here it is 539.24, right? So in order to show, in order to generalize this code, what you have to do, you have to take population randomly, right? Okay. So instead of writing this particular code, let me go for a generalization of the code. So I'm making it comment. This random number is also comment. Let me write a generalized code. So I'll generate the random number for I is equal to 1 to students. For j is equal to 1 to subjects. Okay. Population. Okay. Population. You can directly write without loop also. Population of I comma j is equal to random integer. You have to specify lower limit and upper limit. Okay, I'm right lower comma upper. Here you written lower and upper limit, right? Then 1 comma 1. In each iteration, it is going to take one value. Population is correct only, right? So it will generalize your code, right? Any where we have to change? Yes. Again, when you calculate this random number, Now random number I have commented. So in place of random number, you have to simply write RAND, right? Anywhere we have used random number. Yeah, you have to comment this line. Yeah, it is random number. Anywhere again we have written random number. No, right? So after the end of this loop, just I want to show the value. So for that I need to write a small code. Let my final fitness is I am taking is a big number, which will never reach, so that I will get the accurate value for I is equal to 1 to students. Final fitness. Okay. If I will compare, right? First one. If fitness of I is less than final fitness. Okay. If the value is less, then only you are going to update the final fitness. Otherwise, you need not do anything, right? So is equal to fitness of I. Right. Now I'll show you the display, the solution. So I'll write display. The solution is so I want to show you the final fitness value, right? Okay, let us run for one time. Now the number of iteration is 2, right? Yes, okay, run it and see what is the result we are getting. We got the result is 351.7284. Let us increase the number of iteration to 20. Then you can see here you are getting the value is 0.7396. If I increase the number of iteration to 30, you are getting a very small value. It is not a negative value. It shows that 6.9472 into 10 to the power minus 4. So you are getting 0.0006. Don't take it is a negative value. So the value is 0.0060, right? And if you increase it to 50 iteration, I will get again a very small value, right? 10 to the power 7 means it is almost equal to 0. Right? So this is a generalized representation. Only we have to change the number of students. Let us increase the number of students to 20, number of subject to 5. Okay, you can see we are getting the value as 1.2611 e minus 06. With 50 iteration, it is giving you the value which is close to the optimum value or global solution value, that is your 0. Okay, in this way you can implement the Rao-1 algorithm. Let me paste this thing in the chat box. The first part of the code, second part of the code, third part, because it will not come if I paste the entire code. Fourth part of the code, and the last part of the code. Okay. Copy this one from the chat box, and you can run if you have MATLAB. You can run now, or you can run after installing MATLAB. So you will see you will get whatever result I got in my system, right? And modify this code as per your research domain and see whether your result is good or not. Okay, if you need the research article, I'll show you my reference. Then there you can see reference. Yes. Yeah. If you want this Rao algorithm, you refer to the last one. Okay, the paper name is 3 metaphor-less simple algorithm for solving optimization problem, published in the International Journal of Industrial Engineering Computation. volume number 11, issue number 1, paper 107-130 in the year of 2020.
Sir,
Okay.
please post the paper in the chat box, sir.
Okay, I'll type in the chat box. Rather than the chat box, let me search and give you the exact link. That is better. Meta
It's
4.
better, it's better, sir.
Yeah. It is available in ResearchGate. You can download. And this is that paper you can follow. Whatever I discussed, you can see also in this particular paper. But the code is different. Here also code is given, but the code. Yeah.
Hello.
Yeah, sir.
Sir, with kind permission from you, please can share this paper with us, please?
Yeah. I'll share in the WhatsApp group.
Okay, thank you very much, sir. Sir, another humble request to you. Sir, any particular books or any particular blog that you could suggest us where, the type of algorithm for optimization that we're being taught in this particular FDP program, will be available in much more details so that we can practice for the real life scenario. Thank you very much, sir.
Yeah, you will not get Rao algorithm in any book because it is a recently developed algorithm. But you can, as I already mentioned, neural network, fuzzy logic, and genetic algorithm that is published under PHI Learning Private Limited. That book is there in my slide also, the first reference. That book you can refer for more details about optimization algorithms.
Okay, and they have also provided the application of those algorithms through MATLAB or that kind of softwares.
Code is not there. Theoretical part you will get. Code you have to do your own. Code part I think you will not get in any book.
For code, sir, for code, what sort of applied books are available there?
For code, I don't think that as per my knowledge, there is no book showing the code of genetic algorithm, PSO, and colony optimization and others.
Okay.
You may get theoretical concept, but not the implementation details. Yes.
Okay. So, sir, I know this question might be a bit, absurd, but the fact is that I'm not from the discipline of engineering. I'm actually a management graduate, and right now working in the field of financial engineering. My research interest is on that field. So, sir, any particular book that you could suggest me for optimizations in financial engineering and some applied algorithms through Python or through MATLAB? Thank you very much.
MATLAB. Okay, I'll see it and I'll post in the group. Okay, if I get any book, let me search related to financial engineering. Okay.
Sir, good afternoon, sir.
Yeah, Arun sir, please tell me.
Sir, actually, I am working on the machining and parameter optimization part, sir.
Yeah.
So I have used GA and some of the algorithms. So what is the new existing algorithm which can be used in further, sir? Because
you try with Rao algorithm, sir. In your respective field, I don't think that Rao algorithm has applied. If GA is already applied, you can try with Rao and see that whether the result is good or not.
Okay, fine. Thank you, sir.
You take this the same MATLAB code, only you model as per your problem.
Fine, sir.
The same code will work for you. Only you have to model the input. That's all.
Sure, sir. Thank you. I'll check it, sir. Thank you.
Okay. Any other question, anyone? Okay. Thank you everyone for patiently listening me. We will start the next session at 5:05 as per our schedule. Take a break of 10 minutes.
Good afternoon, all. Am I audible?
Yes, madam, you're audible.
Okay. So good afternoon, all. Once again, I welcome all of you to the day 4 of our program. So in this session, I am going to discuss about artificial bee colony algorithm. So how this algorithm works, right? So what are the phases in this artificial bee colony algorithm? And at the end, we'll see one problem how to solve by using this ABC algorithm. So as we have discussed, like your GA, SEO, and what is your RAW algorithms, right? TLB, all are your meta-heuristic algorithms or population-based meta-heuristic algorithms, right? So here ABC algorithm, this is also a population-based meta-heuristic
Hello.
algorithm. Yes?
Hello. Ma'am,
Yes,
sorry for interrupting. This is Mustafa Shamim Firdaus. Once
yes,
again,
sir.
thank you very much for being available to us today and providing us this excellent lecture from you. Ma'am, my humble request to you is that I'm not an engineer, you know that very well. So this question always does come to my mind that, ma'am, what
Yes,
is
sir.
why do you call it meta-heuristic? So what is heuristic and what is meta-heuristic, ma'am?
Heuristic, right? You are some value. Suppose you are considering this traveling salesperson problem, right? So heuristic means so we are trying to minimize the distance, right? So that distance you can call as the heuristic here. That way. Suppose you
Okay.
are doing the feature optimization we are doing, right? So number of dimension we want to reduce. So in that scenario, you can consider the information gain for the individual features as the heuristic, with respect to which we are trying to minimize the problem or maximize the problem. That is the heuristic. Some heuristic
Okay.
value you have to set for a particular problem that you want to
Okay.
either maximize or minimize.
Okay.
Depending upon that value, you are trying to go to the, you are searching for the global optimum solution with respect to that point.
Okay. Okay. So the value will be available in that particular case, right, ma'am?
That may be available, that may not be available, right? If that is not available, you have to compute that value by using any mathematical expression.
Okay.
That depends upon the
Okay.
problem, which problem you are
Okay.
solving.
Okay.
Okay.
Okay. And what is meta-heuristic then?
Meta heuristic, that is the in the if you apply the heuristic, in some cases you may stuck at the local optimum problem, right? In the meta heuristic means you are trying to escape from the local optimum problem and you are approaching towards the global optimum solution. You will not
Ma'am,
stuck at the local optimum problem. Yes, sir.
okay. Kindly example, please, of meta-heuristic, please.
Meta
For example.
heuristic, right? 1 minute. Meta heuristic means here we have seen the simulated annealing algorithm, right? In the simulated annealing algorithm, on that ball example I have given, in that scenario, right? If you are going always moving towards the better solution, we'll stop at a particular point, right? So we are unable to further explore the search space, right? But if you use the simulated annealing algorithm in that scenario, so we are trying to explore in the inferior solution direction also, right? So in that way, we can escape from the local optimum and we can reach towards the global optimum solution. Is it clear?
Real world example will be better, please. Please.
1 minute.
Okay.
Like that, suppose we are having like this. We want to maximize this problem. Suppose we are having this is the x, right? This is the fx. Okay. So if you want to
Okay.
maximize the objective function, here this will be the maximum value, right? This is the This is the maximum value. Assume this is this one, right? Suppose we are starting from this point. This is my initial position or the initial solution. I am trying the algorithm. I am able to reach up to this point, right? So here, this is the
Okay.
local optima we are getting. Okay, because
Okay.
always we are
Okay.
trying to find out the better solution. We cannot move in this direction because this is the inferior solutions.
Okay.
Okay. So what we
Okay.
will do, right? If we use some algorithms, we will try to escape from this region and we may move towards this region also. That's why after doing a
Okay.
certain number of iteration, we may reach towards
Okay.
this solution. That is
Okay,
the
ma'am.
algorithm.
Okay, ma'am.
Hmm?
So that is why
Okay.
it is called that meta
Yes,
heuristic. That
sir.
is
Yes,
actually
yes, sir.
giving enough
Generally,
freedom
this is the,
to
yes,
move from
yes.
local to the global. Okay. Okay.
Yes,
Thank you
yes,
very much, ma'am.
local.
Thank you very much. It's an
Yeah.
excellent example. Thank you very much.
So this is the ABC algorithm. This is very old algorithm, right? So different variations of right hybrid optimization algorithms are coming with hybridizing this ABC algorithm with other algorithms. So this is introduced by the Karaboga in the year 2005. So for optimizing our numerical problems, right? Numerical continuous objective function is there. We are trying to optimize those problems by using this ABC algorithm. So as we have discussed the ant colony optimization that is inspired by the foraging behavior of real ants. So here the ABC algorithm, this is right, we are mimicking the foraging behavior of honeybees. So how they are collecting the nectar, right, from a food source. So that behavior is mimicked by the optimization algorithm, that is the artificial bee colony algorithm. So generally, when in the ABC algorithm, there are three types of bees are there. One is your employee bee, one is your onlooker bee, and the third one is your scout bee. So three types of bees are there. So here bee means one solution, one particular solution is represented as a bee, right? So what these employee bees they will do, they are associated with a specific food sources. So food sources means that is also a solution, right? And the onlooker bees, what they will do, once the employed bees they are collecting nectar from the food sources, they used to, right, in the life they used to do some type of dance, that is a wrangling dance, right? So by watching the dance pattern of the employed bees, what the onlooker bees they will do, they will try to choose the food source. That happens, right? That's why they are collectively they are moving from the nest to the food source for collecting the nectar, I mean for collecting the honeys, right? And the scout bees they are searching the food sources randomly. So these onlooker bees they are following the employed bees, and the scout bees they are searching for the food sources randomly. So they don't know where the food sources exactly happens, right? They are not following the employed bees or the onlooker bee. So they will source the food sources randomly. That means like we are choosing the random solutions, right? So that is the case of your scout bees. So depending upon these three types of bees, there are three phases in the ABC algorithm. One is your employee bee phase, second one is your onlooker bee phase, third one your scout bee phase, right? So as we have discussed, in the previous slide, there are employed bees, there are onlooker bees, and there are the scout bees. So onlooker and the scout bees, you can call these are also unemployed bees, right? Because they are not directly collecting from a particular food source. Onlooker bees, they are following the employee bees, and the scout bees, they are collecting food sources randomly. So initially, what you have to do, you are generating the random solutions in every algorithm you have seen, the genetic algorithm or the TLB or the RAW, right, or the SEO, whatever we have discussed so far, all the algorithms. So we are generating a population with random solutions, right? Suppose my population size equals to 5. I am generating 5 solutions, C1 to C5, depending upon my suppose dimension D1 to DM. I am generating the solutions randomly within our range, lower bound and the upper bound. Right? So here also we have to food source we have to generate randomly, and whenever the food sources are generated randomly, that we can call as the scout bees. They are discovering the food sources. That is the randomly assignment or the randomly assigning the values to the decision variables of the given problem. Right. So what will happen after the initial or the random assignment of the value to the solutions? The nectar of food sources, right? This is the nectar of food sources. That means how much honey is there in the honey hives, right? These are exploited by the employed bees and the onlooker bees. and they will continue, right? When they will continue to exploit this nectar, of the amount of nectar from the food sources, ultimately at a particular time they will become exhausted. That means the food source will become exhausted because the nectars are going to be exploited by the employed bee and the onlooker bee. So what will happen? Whatever the employed bees or the onlooker bee they are exploiting, right? If they are exploiting the exhausted food source, that means we can call again, that will become a scout bee, and they will again search the food sources randomly. That means that amount of nectar is going to be reduced. So that employee bee or the onlooker bee, again it will convert to a scout bee. Right? So depending, this is the real behavior of the honeybees, how they are collecting the nectar from the honey hives. So in the ABC, in this ABC algorithm, so we are talking about the food source, right? So the position of a food source, it represents a possible solution to the problem, right? So we'll do one example so that you can understand what a bee represents and what the bee is doing with the food source, right? So the position of the food source we are representing as a possible solution to the optimization problem, and we are talking about the nectar amount available in a food source, right? Because this nectar is going to be exploited by the what you call, that is the employee bee or the onlooker bee. So this nectar amount of the food source that represents the quality of the associated solution. We are talking about the objective function, right? The fitness value of that solution. So we are solving the, say, the small the sphere function, f of x equals to summation of I equals to 1 to n xi square. So this affects this objective value or the fitness value, right? This is represented, or the nectar amount corresponds to the fitness value of the associated solution. Right? So the number of employee bees, how to fix the number of employee bee, how to fix the number of onlooker bee, that depends upon the number of food sources, right? So that depends upon the number of food sources. So how to represent the number of food sources? Number of food sources you have to represent as per the dimension or the decision variable dimension of the given problem, right? Because every employee bee, right, they are getting a chance to exploit one of the food source. So the number of employee bees, this is equals to the number of food sources. Right? So here three types of bees, your onlooker bee, employed bee, and the scout bee. So the employed bee, number of employed bee, we are keeping equals to the number of food sources. Similarly, onlooker bee also, this is equals to the employee bee, number of employee bee, and the scout bee, this will vary, right? So how to find out the scout bee, which solution we have to consider as the scout bee, that we'll see later, right, in the scout phase. So the very first phase of the ABC algorithm is we have to do the employee bee phase, right? So here we have to provide the fitness function. So as per whatever we have discussed, right, whatever the algorithms, we are using the objective function, right? For f of x, we are objecting the objective function. So here in the ABC algorithm, right, so instead of the objective function, we are using the fitness function. So the fitness value is determined from the objective value. Right? So there is a simple formula is there. If this fitness value is positive, some formula we have to use. If I mean the fx value is positive, we have to calculate the fitness value by using some formula. And if it is right, if it is negative, if the f of x is negative, then the fitness value we have to calculate by using some another formula. So by using this fitness value, we have to evaluate the quality of the solution. Right? So that nectar amount of the food source, right, in the real life of the honeybees, that is represented by the fitness value of the given solution of the optimization problem. Okay? So what the inputs we want for applying this ABC algorithm, right? A problem, we want an optimization problem, we want the optimization problem for which we want to find out the global optimum solution, right? So what you want to optimize, for that fitness function is required, right? The lower bound and the upper bound of the decision variables are required. As this is a meta-heuristic population-based algorithm, the population size NP is required, right? And the number of iterations T is also required. So this limit is another variable you want, that is used to determine the scout bee. How to find out the scout bee, that is determined by using this limit value. Right? So initially the limit value we have to fix as per the number of dimensions of the decision variable, right? And the population size. Then depending upon that limit value, right, after performing the employee bee phase and the onlooker bee phase, we'll use this limit value to determine whether there is a scout bee phase for the ABC algorithm or we have to discard the scout bee phase. right? So there are 3 phases. Employee B phase you have to do, followed by onlooker B phase you have to do. Then you have to find out whether you have to perform the scout B phase or not. So the scout B phase, right, whether you have to go for that phase or not, that will be determined by using this limit value. So I will explain what is the representation of this meaning with respect to the optimization problem also, right? So as this is a population based algorithm, you are initializing a random population, right? Depending upon our population size, we are generating the random population. So here what happens, in the like your genetic algorithm or the TLV, you are initializing the population size equals to 5. So what we are representing, we are generating 5 solutions, C1 to C5, right? But in the ABC algorithm, when you are representing NP, right? So this number of populations represents the total number of employee B and the onlooker B. So the EB, employee B plus OB, this represents NP. So as I told, onlooker B, number of onlooker B, this is equals to the number of employee B. So if you are fixing NP equals to 10, right? So the number of employee B's will be 5, number of onlooker B is 5. So the total swarm size will be 10. So we are not generating 10 solutions here. If the NP is 10 in the ABC algorithm, if the NP is 10, we are generating, right? Suppose 5 number of initial other random solutions. So always you keep this NP value as a even number, right? So that you can divide among the employee B phase and the onlooker B phase. So that is the difference. Next, what you have to do, you have to evaluate the objective function, and as per the objective function, you have to define the fitness function, because depending upon the fitness function, you are going to determine whether a new solution is better than the old solution or not, right? Then there is a trial counter. This trial counter, this is used for determining the scout B phase also. So initially you have to set the trial counter of all food sources. So all food sources means you represent all solutions, right? This equals to 0, right? So during the employee B phase and the onlooker B phase, this trial counter value is going to be changed, right? So how to change, right? When to change, right? That we'll see through the employee B phase and through the onlooker B phase. When we'll discuss detail about the employee B phase and the onlooker B phase, you can know how this trial counter is going to be changed, right? So as I told you, this limit value will determine whether you have to go for the scout B phase or you have to discard this phase, right? So for that, if your trial, right, if your trial value is greater than the limit value, because we are changing this trial counter when the employee B phase we are doing and when we are doing the onlooker B phase, at that time, right, at the end of the onlooker B phase, you determine for which solutions the trial value is greater than the limit value, right? So the solutions for which the trial value is greater than the limit value, that means that solution is called a scout solution, or that we can call that is the scout B phase. So those solutions we have to discard. That means the limit of the nectar has been reached and the bee is trying to exploit that food source. That is the meaning here. That's where we have to discard that scout bee, or thus we have to discard that solution, and that phase is called the scout bee phase, right? That means that food source, so the solution is already exhausted, so you have to discard that one, you have to create a new solution. That is the meaning, right? So as this is a, right, your iteration based algorithm, so for t number of iterations, you have to perform the employee B phase for all the food sources. Next, you have to determine the probability of each food source. What is the probability that more amount of nectar is there in the food source? That will be determined by using this probability function. After determining the probability, you have to perform the onlooker B phase to generate the new food sources or the new solutions, right? So once you have performed the onlooker B phase, you are memorizing the best food source, right? So the best food source you are memorizing for updating the global solution. Right? So if trial of any food source is greater than the limit, so you have to perform the scout B phase for the exhausted food source. Right? So employee B phase followed by onlooker B phase, then followed by you are checking whether you have to go for the scout B phase or not. If you are not getting, this condition is not satisfying, right? That means the limit of the nectar amount has not reached till now, so no need to go for the scout B phase. Again, you have to iterate for the next iteration. So this is the basic procedure for the ABC algorithm. Now let us see what happens in the employee B phase of the ABC algorithm, right? So what happens generally, if you see, suppose my number of population size I have considered 10. So number of EB, employee B is 5, number of OB is 5, right? So what we are doing, we are generating 5 solutions randomly. This is the solution 1, this is the solution 2, this is the solution 3, this is the solution 4, this is the solution 5. So solution means what represents? Suppose we are having D-dimensional problem, right? So the values of the D decision variables are given like this. The value, suppose this is a 3-dimensional problem. So 3 values are given, x1, x2, x3 for all the solutions and given. We are generating randomly. Initially we are generating randomly. So what will happen in the employee B phase? We are trying to generate a new solution for every solution present in the population. That is the meaning. That means every solution will go the employee B phase. That means we are trying to modify every random solution by using some mathematical formula. So here what we are doing, 1 EB1, there are 5 employee Bs, right? EB1, EB2, EB3, EB4 and EB5. So we are assuming that every solution is going for the employee B phase. So let us assume EB1 is associated with S1, EB2 with S2, EB3 with S3, EB4 with S4, EB5 with S5, right? So what will happen? So solution 1 will go for the employee B phase, S2 will go for the employee B phase, like that S5 will also go for the employee B phase. So what will happen in the employee B phase? We are trying to modify one of the decision variable value in the solution S1. Randomly, we are trying to modify one of the decision variable value in the solution S1, right? Somebody has unmuted. Please mute yourself. Okay. So number of employee B phase, this is equals to the number of food sources here. So all the solutions get an opportunity to generate a new solution in this phase. So S1 will go employee B phase and it will generate a new solution S1 dash. S2 will go employee B phase and it will get a new solution S2 dash. Similarly, S3 will go for employee B phase. It will generate S3 dash. S4 will generate S4 dash. Then S5 will generate S5 dash, right? Like same your whatever we are doing the other optimization algorithms, then you have to compare if S1 is better or S1 dash is better. So whichever is better, that solution you have to keep, right? And how to determine the better? Again, it depends upon whether you are going for the we are going to solve the maximization problem or minimization problem. The better solution will be determined differently with respect to maximization and the minimization problem, right? So what we have to do for converting this S1 to S1 dash? So that is our employee B phase, right? That means the solution S1 is undergoing employee B phase to generate the solution S1 dash. So what happens in the employee B phase? Only one decision variable value in S1 we are changing to convert it into S1 dash, right? So if the D number of decision variables are there, which variable we have to change? So that will be determined randomly, right? So let us see what is the mathematical equation behind this employee B phase. So here we have assumed that so every solutions will get an opportunity to generate a new solution, as I have shown you from S1 to S5. They are generating S1 dash to S5 dash. So how they are undergoing this employee B phase? So you have to generate a partner, right? Or you have to select a partner randomly to generate a new solution. So if you want to apply the employee B phase to the solution S1, you have to generate a partner out of S2, S3, S4 and S5, right? Like your differential evolution algorithm, if you remember, right? When we are doing the mutation, we are generating 3 random solutions for the rand DE rand 1, right? So those 3 solutions are different from each other as well as different from the current solution. So here we are selecting a single partner, right? So single partner we are randomly selected to generate the new solution. And what is the constraint you have to follow? The partner and the current solution should not be the same. So if we are trying to apply the employee B phase to the solution S1, So you have to select a partner out of S2, S3, S4, and S5. Right? So partner you have to select, and the partner and the current solution should not be the same. Next, what I told one bit or one decision variable value you have to change from a solution, right? So which solution you have to, which variable you have to change, right? So randomly you have to consider the variable. Suppose that variable is j, right? So jth variable you want to change. So jth decision variable you have to change. So from where you will get the j value? So j is the value randomly you are choosing from 1 to 8, 1 to d. So d dimensional variable is there. So j value you have to select so that j belongs to this 1 to d. So that bit only you are going to change. Suppose our solution, we are having three decision variables x1, x3, x2, s3, right? So suppose I am choosing j equals to 2. That means the x2 value of s1 will be changed only for the s1 dash. Remaining x1 and x3 will be same, right? So what is the mathematical equation you have to use here? Like your differential evolution algorithm. So the new solution is generated by modifying a randomly selected variable. Assume that randomly selected variable is jth, right? So xj new, that means the second bit we are trying to modify. So what is the updated value of the second? That's why xj new. Okay. So xj new will be determined by what is the old value of this value. Suppose for this, suppose assume 1, 2, 3, right? So I want to change this variable only. So what is the old value? 2, right? Plus phi is a constant that is in the range -1 to 1 multiplied by, right, old value minus the jth bit of the partner, right? So let us 1 minute, just give me 1 minute. Okay. Suppose we are having x1, x2, x3. These are the three variables. This is the solution 1, solution 2, solution 3, solution 4, solution 5. Randomly I am writing in the range 0 to 10, 1, 4, 8, 5, 6, 7, 3, 4, 5, 2, 3, 2. Assume this is the randomly I have generated, right? Now this S1 I want to apply the employee phase to the S1, and this bit I want to change, right? And suppose the partner I have to select, suppose partner I am selecting as S3. So how to write this one? Now S1 dash we have to write, right? S1 dash new solution will be, so there will be change is the second bit only. First and third bit will be same. So what is this bit now? So S1, right? S1 dash for the second bit, this will be previous value or the old value is 2 plus 5 value you have to choose in the range -1 to 1. Then the old value is 2 minus jth bit of the partner. So this is the partner and the jth bit of the partner is 6. 2 minus 6. So depending upon the value of 5, the range -1 to 1, something you will get here, right? If you do the calculation. So that value will come here, right? Now S1 is 1, 2, 3. And after applying the employee V phase, we are changing the second bit of the S1 as that value, suppose something like suppose 0.3. Assume. So this is 0.3. Now S1 is undergoing employee V phase to generate a new solution 1, 0.33. Now you have to decide which one is better, whether this one is better or that one is better. So for that, we have to calculate the fitness function, right? So that simple mathematical equation we have to use, like your mutation operator, right? So xj new is the jth variable of the new solution. Xj is the jth variable of the current solution. This is the jth variable of the partner, and the partner and the current should not be same. Phi is a constant in the range -1 to 1. And after doing this mathematical operation, you have to do the bounding, right? If that value is out of range, right? Because we are fixing the LB, lower bound and the upper bound is out of range, you have to forcefully make it to UB if it is exceeding this part. And if it is coming beyond LB, you have to forcefully keep this value as LB. So bounding you have to do this one. So this is the simple employee V phase. You have to generate new solution for every solution present in the population. So you have done for S1, right? Next you have to do for S2 again. Again S2 will generate another solution. S3 will generate another solution. S4 will generate another solution. S5 also generate another solution. So every solution there is a chance that they are trying to generate a good solution. That means they are exploring the search space by doing the employee V phase, right? So this is the simple pseudocode of the employee B phase. Similarly, your input would be fitness function, lower bound, upper bound of the decision variables, population size. So depending on the population size, you divide by 2, you will get the number of employees. What is the fitness function and what is the trial value, right? So what we are doing for every solution in the population, this is the I NP by 2. Sorry, this is not NP, NP by 2. For I equals to 1 to NP by 2, what you are doing? You are randomly selecting a partner such that I not equals to P. So the partner and the current solution are different. Then you are randomly selecting a variable J because the Jth variable only you are trying to modify, right? By use that equation. I tell na xj dash equals to old xj plus phi into xj minus xpj, partner jp. So use that formula and you modify the jth variable. Then what you have to do, you have to do the bounding, right? If this is beyond the LB and the UB value, you have to do the bounding. Next, you have to select, right, whether x1 is best or x1 dash is best, right? So for that, you have to evaluate the objective function, right? You have to find out what is the, I told you have to calculate the fitness value in the ABC algorithm. So what is the fitness of new and what is the fitness of old, right? If the new solution's fitness is greater than the fitness value of the old solution, you have to accept the new solution. Otherwise, you have to keep the old solution, right? So whenever x1 dash is a better solution than x1, in that scenario, you have to set the trial value of that food source equals to 0, right? Because we are using a trial vector. So what is the meaning of trial here? One solution, it is trying to explore the search space and it is able to get a good solution. In that scenario, you reset the trial value equals to 0, right? Suppose x2, we have applied the employed B phase, we generate a new solution x2 dash, but x2 dash is not a good solution, right? So that means this food source or this solution undergoes employee B phase and it is unable to generate a new solution. That means its trial value you have to increment by 1, right? If this is a good solution, the trial value you have to make as 0. If you are not getting good solution, the trial value you have to increment as 0. That means failure. This solution tried to generate a new solution, but there is a failure occurs. So how many times that failure occurs? That is represented by the trial. So that is the meaning of the trial, right? If you are getting the good solution, you have to reset the trial value equals to 0, right? Otherwise, you have to increment the trial value of that food solution or the food source by 1. Right? So this is the simple employee B phase. So once you have done the employee B phase, now we have started with a NP by 2 population, right? Population, I mean the Bs. Now after applying the employee B phase, again you will get the same NP by 2 number of solutions, right? Once you get this one, then what you have to do, you have to perform the onlooker B phase. So before doing the onlooker B phase, you have to determine the probability value of individual solution, right? So what is the probability value of that solution? So probability value of the each solution to undergo the onlooker B phase, right? So depending upon this probability B value, the onlooker B on the onlooker phase happens, right? So the probability of ith solution is 0.9 into fit of I, fitness value of the ith solution divided by maximum fit plus 0.1, right? So this solution it is written such that the probability value depending upon the fitness value of that solution with respect to the maximum fitness in that population, right? So always if you use this equation, this value, probability value, always it will come in the range 0 to 1. So what is the meaning of this probability value? So solution with higher fitness value, it will have higher probability, right? So the fitness solution may undergo onlooker phase for more than once. If a solution is having the higher probability, so the onlooker phase is designed in such a way that higher probability solutions, they may able to generate good solutions by applying the onlooker phase. So that is the meaning of this probability calculation, right? So after doing the probability calculation, what we have to do now? Now again we are having, you see, S1 is there, S2 is there. Assume S1 dash after doing the employee B phase. S3 dash is there, S4 dash is there, S4 5 dash is there. These are the 5 solutions we got after the employee B phase, right? Now how many onlooker Bs are there? Again the number of onlooker B. Suppose OB1, OB2, OB3, OB4, and the final is OB5. So there are 5 onlooker Bs. So what happens? This onlooker B1, it will try to exploit one of the food source from this set, right? So what happens in the onlooker B phase? As I told, every solution we are having some probability value. So the probability value we have written here. Suppose P1, P2, P3, P4. We have calculated, right? P5 by using the previous equation. We have calculated the P1. Now what happens? We will try from the OB1, right? So OB1 will try to exploit which food source. So what it will do? It will try to exploit from the first solution, right? Whether it is able to. That means after undergoing the onlooker B phase, so whether it can exploit this food source or not, or if it is able to exploit, then we have to change the solution S1 dash, right? So how to determine whether this OB1 will exploit the solution S1 dash or not? For that, you generate a random number. So that is follows the uniform distribution in the range 0 to 1. If this R is less than the probability value of the solution S1 dash, then S1 dash will go for the onlooker B phase, right? So onlooker B phase, if S1 dash you are going for onlooker B phase, same thing you have to do like your employee B phase. You have to generate a partner, right? You have to determine with bit or with decision variable you have to change, and we have to use the same mathematical equation that new value jth bit new value equals to old value plus phi into old value minus the partner value. That equation you have to apply, whatever you have done in the employee B phase. Assume this R is greater than the P1. So what will happen? If R is less than P1, this OB1, that means this S1 dash is able to undergo the onlooker B phase, right? If this R is greater than P1, if R is greater than P1, that means this OB1, it cannot exploit the solution S1 dash. That means S1 dash, it cannot be changed, right? That is the meaning. So what you have to do? OB1 again, it will search for the next solution, S2 dash, right? So for that again, you generate a random number. If R is less than P2, then S2 dash will go for onlooker B phase. And again, same thing you have to do. You have to select a partner. You have to select the variable, which variable you have to change, and you have to apply that mathematical equation. Suppose again this R is greater than P2, right? So this also, this OB1 also, it cannot exploit the S2 dash, right? So what it will do? It will check for the S3 dash. If suppose R is less than P3, again you have to generate a random number. If R is less than P3, it will exploit the S3 dash, right? Suppose it's over. OB1 is able to exploit the S3 dash. Next, this over for the OB1 over. Next OB2, this B will try to exploit one of the solution. Now from S3 dash, with the previous onlooker B, it exploited the S3 dash. So OB2 will start to exploit from this fourth solution, right? Because OB1 exploited the third solution. So next B, OB2, it will exploit from the fourth, right? Again, same thing you have to apply. If R is suppose greater than P4, so it cannot exploit this food source. Again, it will search to exploit the next solution, that is the fifth one. Suppose this is the R is here less than P5. So it will exploit this one. Now for the onlooker B phase, over for the second one. Now OB3 is there. Now you see before OB2, OB2 exploit the fifth food source, right? Or the fifth solution. So from where OB3 will start? Again, OB3 will start from the solution S1 dash. Again, the same procedure will be repeated up to every solution undergo the onlooker B phase, right? So this is the onlooker B phase concept. So let us see how it works. So same thing we are applying the fitness function, lower bound, upper bound, here NP, population size, probability. Here we are getting the probability because this depending upon the P value, we are deciding whether that onlooker B phase we have to go for the undergo for the onlooker B phase or not, and the probability and the trial. Okay. Now you see here this part. While m is less than equals to np, so we are setting the value of m equals to 0, n equals to 1. So n for the first solution. Okay, we are trying to explore the first solution. So while m less than equals to np, what you are doing? You are generating a random number. If that random number is less than the probability n, we are trying to go for the employee B phase. Now if you see this one, this part, whatever we have done, same thing is written, whatever we have done in the employee B phase. We have selected random number P such that the partner and the current solutions are different. Randomly select the variable J, modify the Jth variable, then you bound the variable, right? Depending upon the lower bound and the upper bound, then you determine whether you have to accept the new solution or you have to reject the new solution. And depending upon the accepting the new solution, right, you have to set the trial equals to 0 if you are getting a better solution. If you are not getting a better solution, I mean you are keeping the old solution, then you have to increment the trial of that solution by 1, right? Next, what we are doing, we are incrementing the value of m equals to m plus 1. That means if OB1, this is over for S1 dash, right? Next, we are going for the OB2. That's why m equals to m plus 1. Okay. After that, your n equals to n plus 1, why we are keeping? Once we have, right, once we have done the onlooker B phase for a particular solution, then we have to search for the next solution. Like here we have seen the once OB2 has explored S4, then OB3, it will start from the OB5. Right? That's why your n equals to n plus is there, right? So once your S5 is over, again write the next OB, right? It will start from the first solution. That's why you have to reset the n value if the value is greater than the number of non-looker B phase. Right? So these are the steps you have to follow for the onlooker B phase. So employee B phase, you are doing same, your jth bit you are changing for a particular solution, right? By using that mutation operator like your differential evaluation. And in the onlooker B phase, for doing the onlooker B phase, you are calculating the probability value of individual solution. Then depending upon the random number generation, you are determining how the solutions are going for onlooker B phase. And when we will solve an example, you can understand what is actually happening in this onlooker B phase and how the solution space is going to be changed, right? Now what we have done, I told that the first, in the ABC pseudocode of the ABC, there is a parameter limit, right? So that is the user specified parameter. So depending upon this limit value, we are determining whether you have to go for the scout phase or you have to discard the scout phase, right? So generally, suppose the number of cycles T, number of generations. Swarm size S means your number of population is NP, right? So limit is a user specified integer value. So every solution, as we have seen, right, we are having a trial count associated with every solution. If the solution is able to generate a better solution after performing employee B phase or after performing onlooker B phase, so we are resetting the trial counter as 0. If we are not getting better solution after doing the employee B phase or after doing the onlooker B phase, we are incrementing the trial counter by 1. Right? That means for every solution there is a trial value. Right? So either the trial value is 0 or it may be greater than 0. Right? So if the value of trial counter is greater than the limit, the solution can potentially enter into the scout phase. Right? So that means that solution we are going to discard from the current population. So the trial counts of abandoned solution is reset to 0 and we randomly you have to generate another solution in place of that scout B. Right? So how to find out that scout D, we'll see in the example. So generally the limit value, this is a user specified parameter. So the limit value is fixed as your population size into dimension of the decision variable. So NP into D. Right? So these are the things you have to take care when you are initializing the ABC parameter. So the scout phase, it may happen, it may not happen. It depends upon the trial value and the limit value of the given problem. So solutions with trial value greater than the limit value, right? These are candidates to be discarded. That means the nectar amount in those food sources has been exhausted. So you have to discard those food sources. You have to remove those solutions from the current population. That is the meaning, right? So if you are discarding that solution, you have to replace that solution with a new solution, right? So that new solution you have to generate randomly. So one solution with trial greater than limit is replaced with a new random solution. And what is the trial value of that new random solution? You have to keep it as 0, right? So this phase, after doing this scout phase, again you have started with n by 2 number of solutions. After doing the employee B phase, again you are getting n by p number of solutions. After doing the onlooker B phase, again you are getting n by 2 number of solutions. Again, right, if you are performing the scout B phase, it depends whether you have to perform or you have to right, you have to skip the scout phase. Again, you will get NP by 2 number of population. So we have started, suppose, from 5 solutions, right? So after performing employee V phase, onlooker V phase, and the scout V phase, again you are getting another 5 solutions, right? So this is the first iterations population, and after undergoing 3 phases, again we are getting another solution. Now, if you see in one iteration, suppose in this solution, whatever solution, if this is a minimization problem and the value you are getting as 10, right? In the next iteration, always, right, it may happen that you will get the minimum value or the less value than this 10. Suppose 8, 9, something, right? So in the scout phase, one thing you have to do, sometimes what will happen, right? The best solutions, they are having the trial value greater than limit. So best solution we have to replace at that time. So for that scenario, in order to skip the best solution, you have to memorize that solution. That means you need to store that best solution in a particular variable. So what you have to do in the scout phase, same thing we are providing our fitness function, lower bound, upper bound, trial, limit, P, right? So you have to identify a food source, I mean the solution, right? Which trial is greater than the limit. So that is the abandoned solution. You have to discard. So you have to replace the escape from the population P. P is the population, sorry, small p, right? So how to generate a random population? This is simple. As per randomly we are generating now, depending upon your LB and the UB value. So LB plus UB minus LB into R. So this is the random solution. You have to replace that abandoned solution with this solution. Right? Then you have to evaluate the objective function, fitness function for this solution, and you reset the trial value equals to 0. Right? Again, you will get a new set of population. Right? So for that new set of population, again you have to iterate for the next step of the ABC algorithm. Again, you have to do the employee V phase, onlooker V phase, and if it requires the scout V phase. Right? So one thing you have to do during the scout phase, that is, you have to memorize the best solution also, right? So that I will explain through the example. You have to memorize the best solution in every iteration, so that information we are not losing, right? So after doing the 5 iterations, right, whatever best solution you are memorizing, that will be your optimum solution for the given problem. Now we'll see how this algorithm works. For the same sphere function we'll use, and we'll apply the employee V phase, onlooker V phase, and the scout V phase, and I will see how the population is changing, right? From one iteration to another iteration, how the population is changing, and what about the fitness function? I mean the objective value, how it is changing from one iteration to another iteration. We'll see this example, same the sphere function we consider f of x equals to your summation of x I equals to 1 to 1 xi square, right? So we'll consider the dimension d of the decision variables equals to 4, lower bound equals to 0, upper bound equals to 10, right? So the objective function we can write as the decision variables are 4, f of x equals to x1 square, x2 square, x3 square, x4. So we have to add this. Okay. So we are having 4 decision variables, x1, x2, x3, x4. So what you have to do now, you have to solve this problem by using ABC algorithm, right? So what you have to do, you have to initialize the parameters of the ABC first, right? So what is the what is the population size, how many employee bees are there, how many onlooker bees are there. First thing we have to do that one, right? How many iterations you have to iterate the ABC algorithm, that is also required. So these are the parameters for the ABC algorithm. We'll see. So assume the swarm size equals to 10. Swarm size S means your NP, right? So if the swarm size is 10, right? So what will happen? Your number of bees, employee B equals to 5, number of onlooker B equals to 5. So that the total bees size will be 10. So EB equals to 5, NB equals to 5. So this S means your NP only. Okay. Depending upon the S number of swarm size, that NP number of food sources you have to define. That means your S equals to NP. You can assume that. Okay. Either you define the swarm size or you define the what you call population size. Same thing. But you have to divide by 2 to generate equal number of employee B and the equal number of OB, onlooker B. And suppose the number of iteration equals to 10. So we are not going to go for the 10 iterations. So we will solve for only one iteration because some hand calculation we have to do, right? Generally, I told NP limit equal to NP into D, right? So for this hand calculation, simply I am fixing the value limit equals to 1 so that you can see which solution is abundant and what is the require if scout V phase we are going to cover or not. And if we are entering into the scout V phase, what we have to do with that abundant solution. So for that purpose, I am keeping the limit value equals to 1. Otherwise, whenever you will simulate, you fix the limit value equals to NP into D. So for this particular problem, your NP size is 10, D is 4. So you have to fix the limit size equals to 40. Right? This is the fixing the value of the limit. Now let us see what we have to do. The same thing I told, if the food swarm size equals to S equals to NP, right? So this is the number of employed bees and the number of onlooker bees equals to 5. Right? This is the EB. EB equals to OB equals to 10 by 2 equals to 5. That means 5 solutions we have to generate randomly. Okay. Now, let's see. So next we have to generate the random solutions. How many random solutions we have to generate? 5, because our EB and OB equals to 5. Okay. So generate 5 solutions within the domain of the decision variables. So the domain of the decision variables we have not considered here now. Okay. Here I have written 0 to 10. LB is 10. Sorry, LB is 0. UB is 10. So if you see here, this table it represents, this is the population P. So now relate the food sources. So this is the food source 1, food source 2, food source 3, food source 4, food source 5. So each food source represents a solution for the problem, right? So food source is the solution for the optimization problem. So what is the dimension of the given problem we have considered? 4, x1, x2, x3, x4, right? Now if you see, we are generating randomly the value of these 4 decision variables. All the values are in the range 0 to 10. All the values you can see. All the values are in the 0 to 10 because we have to satisfy that constraint also, like all the decision variables value, they will take the value in the range 0 to 10. Okay. So this is the random population we have generated. Next, what we have to do, we have to find out the objective function value. So objective function, what is that? F of x we have written summation of I equals to 1 to n xi square. As these are the 4 variables are there. So how we are getting this 81? Same thing here, 4 square. Like your differential evaluation algorithm also we have solved the same problem, right? 4 square, 0 square, 1 square, 8 square. So 16 plus 0 plus 1 plus 64. Okay. 65 plus 16, 81. Like this, you can find out the objective value of the individual solution. Right. Next, what I told you have to replace, right? Because all the objective values are here positive, so there will be no effect or there is no difference if you use the fitness value or the objective function, right? If the sum of the objective functions are negative, in that scenario, where fitness will be benefit, right? So that in the ABC algorithm, always you try to find out a better solution with respect to the fitness of the solution. So fitness, how will you determine? So the fitness will be 1 by 1 plus f. F is the objective value, right? If f is greater than or equals to 0, determine the fitness value as 1 by 1 plus f. If this is less than 0, so you determine 1 plus absolute value of f. Right? Here we are getting all the positive values for this problem, right? So no problem. So this condition is not coming. So if you use the objective value or you use the fitness value, you will get the same, right? Because fitness will be reversed, right? Because this is a minimization problem. So we are taking the fitness, right? 1 by 1 plus f. So you have to take the reverse whenever you are choosing the better solution. Now you see, by using that formula, what I have done, same. This is the random population. Objective function value we have calculated. Next, the fitness of the population we have calculated by 1 plus f, right? Let us see for this one. 1 by 1 plus 81. If you divide 1 by 82, you will get this value only. Right? Like that, you do this is 1 by 1 plus, directly let me write 1 by 141. This is 1 by 36. And this is 1 by 103. This is 1 by 70. So these are the values, fitness value for the individual solution. Right? So these things you have to do. Next thing, if you remembered, we have kept a trial value, right? Trial value we are associating for every solution. And that trial value we are resetting or incrementing by 1 after every employee B phase and after the every onlooker B phase. So you have to maintain a trial value for every solution in the population. Now if you see in the next table, So you have to generate the trial vector of the population. So what it represents? It represents the number of failures encountered by the particular food source. That means the solution this is undergoing employee B phase or onlooker B phase, but it is unable to generate a new solution. That is a failure by that food source, a failure by that solution. Right? So initially we have assumed we have assigned the values as 0. So the trial value of the solution, first solution up to the fifth solution, these are 0. Okay. Next, what we have to do? Now our target is to perform the employee B phase. Everything we have initialized. So for simplicity, we have initialized the limit value equals to 1, right? Because if I will keep the limit value equals to 40, I have to do a large number of iterations. So I cannot show by hand calculation, I cannot show those things, right? That's why I kept the limit value equals to 1 so that we can know whether to perform the scout B phase or we have to discard. Okay. So trial value we have fixed. Next, what we have to do? You have to perform the employee B phase. So this is the phase 1 of the ABC algorithm. Now what we are doing in the employee B phase? So the first solution is 4018. So this solution will undergo employee B phase to generate a new solution, right? So the solution is now 4018. So this solution we are going to change to another solution, right? So how to do that one? For that, I have to determine which bit I am going to change. Suppose I am going to change this bit, this third bit, right? That means if this is the S1 new solution, so after doing the employee B phase, we will get the S1 dash. So this is a 408. These 3 bits will be same. Only there will be a change in the third bit, right? So how to determine that bit? Already we have wrote the equation, right? We have to choose a partner. Suppose the partner is, assume this one. Partner, we are choosing this one because the partner should be different from the solution. If this is the partner, so what is this third bit? Third bit is 4 here. This is the, right? And suppose the phi value is -1 to 1. Suppose I am assuming 0.5. I have to assign randomly this one. So what is this new bit? Now S1 dash third bit, right? S1 dash third bit, you can write 1, 3. This equals to old value. Old value is 1 plus phi value is 0.5 into old value is 1 minus partner value. Partner's third bit value is 4. So if you solve this one, this equation, you will get some value. Assume that value is 0.7. Assume. So this new solution, right? This is the new solution. So third bit will only change after doing the employee phase. So this is the 4, 0. This is the 0.78. So this thing you have to do for all the solutions present in this population. So this example I have shown for this 4018. Similarly, you can have to go for the second solution. You have to generate a new solution for the third solution, for the fourth solution, for the fifth solution. Because in the onlooker employee phase, every solution will get a chance to undergo changes. Right? Now let us see. So these are the some concepts. So first employee B phase for the first solution, right? So perform employee B phase for the X1 4018. Now you select a random variable. Suppose the variable is third variable, right? Whatever we have discussed. Now you choose a partner. Suppose the partner is fourth. This is the 2149. If you see the table, you will get that one. 2149, right? So for the 2149, now you apply this equation, right? So for that you have to initialize the phi value. If phi value is 0.8, now new value we are getting. So previously it was 4018, right? Previously it was 4018 first solution. Now it undergoes employee B phase and we are getting 40 minus 1.438, right? So this is out of range, right? That lower bound, it is coming beyond the lower bound. So you have to make this as 4008. So the first solution was 4018. After going the employee B phase, you are getting 4008. If you see, only there is a change in this bit only. Right? So whether you have to accept this one or you have to reject this one. As you know, this is a minimization problem, right? This is a better solution. That means for the next population or the next phase, right? Instead of S1, you are writing S1 dash, right? Because this is a better solution than this one. So what you have to do with the trial value of this first solution? If this is a better solution, the trial value of that solution will be remain 0 only. You have to reset to 0. Now let us see here. So this is the bounding. Okay, you have to check the bound condition minus 1.43. This is beyond 0, right? So this is not satisfying the constraint lower bound. So you make it to 0. Then you calculate the fitness value. As this is a right, all the positive objective value we are getting, you can consider the objective value also. If you take the fitness value, if the fitness of the new value is greater than the fitness of the old value, we can consider that is a better solution, because we are considering 1 by 1 plus f, right? Otherwise, if this for this type of problem, you can consider the objective value, right? Like your minimization and the maximization. So if you see, if this new value of the fitness value is greater than the fitness value of the old value, that means whatever new solution you are generating, that is the better than the previous one. So you have to reset the trial of 1 equals to 0, right? Now you see the next table here. So what changes we are getting here? So here previously we have done the employee B phase for the first solution, and we got a change here, right, in the third bit, right? Previously, if you remember, it was 81, now we are getting 80. So this trial counter, it remains same, 0. So now it completed the employee B phase for the first solution. Yeah, now quickly we'll see for the second, third, fourth, fifth, what is the, right, whether the new solution is better or not, and what is the value of this trial count, right? So the next solution is 3197, right? So here 3197 is the second solution, right? So these are the random things. You have to select the which bit you have to change. Assume the first bit or the first decision variable you have to change. Assume we have selected the partner randomly, that's the third solution, and phi you have considered 0.19. Then you have to create the new solution. Same formula you have to use, right? New equals to old plus phi into old minus x of partner. If you do that one, you will create a new solution. Then you have to bound the solution if it is coming beyond the, or it is not following the LB and the UB, right? You bound the solution, then you perform the greedy search. That means whether you have to consider the x2 old value or you have to consider the x2 dash new value, right? That is the greedy search. Then you have to update the solution and you have to update the trial. So these things you are doing for every solution in the population of the employee B page. Right? Now let us see if you take this parameter. So I am not going to calculate. You can verify later. So what will happen here? There is no change in the second solution. That means after doing these operations with respect to these random values, your x2 is better than the x2 dash, right? X2 is better than the x2 dash we are getting. Right? That means X2 undergoes the employee B phase, but it is unable to generate a new solution. So what you have to do, you have to make this trial counter as 1. You have to increment the trial counter as 1. So that you see for the second solution, the previous value is there, your 3197 is there. 3197 previous value is there. Okay. And this trial counter, if you see, this is 1. Okay. It is 140. Previously also it was 140. Right. So this completes the employee B phase for the second solution. So quickly I will tell the third one. So the third solution, this is suppose 0315. Now let us assume the first decision variable you want to change. Partner is 1, phi is 0.56. Same thing you have to do. Create new solution, bound the solution, greedy search you have to do, and you have to update the solution and try. If you apply these things, if you apply with these random things, what will happen? If you see, for the third solution also, you are not able to get a better solution. Now, if you see, same solution you are keeping here, with the trial counter, you are incrementing by 1. Previously, it was 0, now it is incremented to 1. So, with this, your employee B phase for the third solution is over. Now you go to the fourth solution. Similarly, you take the variable 2, partner 3, 5 minus 0.6 and perform the same steps. New solution, bound solution, greedy selection, update the solution and updating the trial counter. So what you will see here also for the fourth solution, as per the randomly, this we have taken, right? Random bit, random partner, and the phi value also randomly. We are also not getting a better solution for the fourth one. So what will happen here? Now see, there is the increment in the trial counter. this completes the employee B phase for the fourth one. Now we have to do the same thing for the fifth solution, right? 1283. Again, random variable 4, partner 3, 5 0.81. Same thing we have to do, same steps we are doing. And what we are doing here, we are observing that the fifth, whatever X5 we have applied the employee B phase, we are generating the S5 dash. So this is a good solution. So now you see here, in this red points, this represents the good solution. Huh? We are changing this one. So this trial counter we have to set to 0. Right? So with this, your employee B phase overs for that particular problem. So for the 5 solutions, we have applied the employee B phase and we are able to generate, either we are returning the old solution or we are generating a new solution. For what we observed that for the first solution and the fifth solution, right? We are generating a new solution. Here it is changing third bit, here it is changing fourth bit. But for the remaining second, third and fourth, old solutions only we are keeping. Right. So we have started with this random population with 5 solutions. Now after doing the employee B phase, again we are getting how many solutions? 5 solutions. But here we are getting, I think, 70.9 something. And previously we were whatever the getting 10. Right. So this new solutions and the good solutions we are adding into the population. Next, what we will do, we have to perform the onlooker B phase. So performing the onlooker B phase, I told you have to calculate the probability value, right? So depending upon the fitness value and the maximum fitness value, we have to calculate the probability. So that equation I told already. So this is the probability value for individual solution in the problem. If you see the trial value, whatever we have obtained, 0, 1, 1, 1, 0, after the employee B phase, that is there only, right? Now let us apply the onlooker B phase to the first solution now, right? So perform the onlooker B phase for the first solution. So the first solution is 4008, 4008. Now you select generate a random number 0.39. So this 0.39 is less than 0.5, its probability value. That means we'll exploit this first food source. That means this solution will undergo the change. So how to do that change? Again, same thing you have to do as per your employee B phase. To find out which variable you want to change, that is the J, which bit, what is the partner, what is the phi value, then create the new solution, right? If you apply these things, you will get 5.96. So X1, previous one is 4008. Now you are getting, what is the value you are getting? 40096. As this is a minimization problem, you can see this is a better solution, right? So you have to perform the greedy search for that one. So if you know that, after performing the greedy search, your X new is better than the X new 1 is better than the X1. So you have to reset the trial to 1, it's 0. Right? Previously it was 0 only, now also it will become 0. But there is a change in this bit now. So this value you see, that is, right, this is going on changing. Right? Better value you are going. So Tx is, this trial value of the first solution is 0. So with this, the onlooker B phase for the first solution is over. Now we have to try for the second solution, right? 3197. So onlooker B phase for the second solution. Again, this is the 3197 is the solution. Generate a random number 0.2. So 0.2 is again less than the probability. That is, probability is there in that previous table, 0.33. Okay. So it will exploit the second food source. That means there is a chance that we will get a better solution from this solution. So we have to mutate that solution. Again, you use the same mathematical equation, right? So for that, which bit you want to change? What is the random partner? What is the phi value? Same things you have to apply here. New solution, bounding, evaluating on reselection, then updating the solution and the trial counter, right? If you apply these things, right, if you perform these 4 things for the second solution, you will get a good solution. That means for the second solution, whatever the X2 was there, after applying the onlooker B phase, you will get X2 dash is better than X2, right? That's why you see you are resetting the trial counter to 0. Previously it was 1, if you remember, it was 1. Objective value was 140. Now after doing the what is that onlooker B phase, now you see objective value is 131.34. That is a better solution, right? And this trial counter, that's why you are resetting to 0, right? Same thing you have to repeat for 3. Same thing, food source, random number, generate the random number, suppose 0.571. The same thing, you are exploiting the third food source. Again, random partner, random variable, which bit you want to change, 5 value. Again, same 4 steps you are doing, right? Here also, what will happen? X3, you are applying the onlooker B phase to X3, you are generating X3 dash, but X3 dash is not a good solution. So the old solution you are returning with the trial counter, you are incrementing by 1. Previously it was 1, now it is incremented by 1, 2, right? Now I will show you another. If your R is greater than P, what we have to do, right? So fourth case, that is that condition is there. So now you have to perform the onlooker B phase for the fourth solution, right? So the fourth source selected is your 2149, fourth one. Okay, we are selecting a random number, suppose 0.95, but this 0.95, its probability value is 0.41. This is calculated for the solution 4, right? So with this food source, so that this solution cannot undergo the onlooker B phase, right? So there is no chance to change this solution, right? So what we have to do? So the B will not get a chance to exploit the fourth food source. So it will check for the next food source, that is the fifth food source. So we are applying the onlooker B phase for the fourth solution now, right? So for the fourth, we are unable to explore because this R is greater than P value. So it will try to explore the X5, right? So but this is the onlooker B phase for the fourth solution. So the food source selected equals to 5, right? 128, 1.38. This is the value. Okay. Now generate the random number. So this random number, if this is less than this probability value 0.55, so it will exploit the fifth food source. Again, you have to do this mutation operator, right, to change that jth bit of the fifth solution. Okay, so assume the random variable to change, this is the variable is 1. Select a random partner 2, right? Phi is 0.7. Then you create the solution, generate the bound, evaluate fitness function, greedy selection, update solution, and try. So what will happen here? You will get that for the fifth one, right? Onlooker B phase we are doing for the fourth solution, but it is exploiting the fifth solution, right? So we are getting a better solution. That's why, right? Here you are getting a better solution, right? So its trial value you are resetting to 0, right? So with this, your onlooker B phase for the fourth solution is over. But till now, your fifth solution, you have not performed the onlooker B phase, right? So you have to perform the onlooker B phase for the fifth solution. But we have explored up to the fifth solution before the onlooker B phase of fifth solution, right? So X5 already we have explored. So again, it will come back to X1. So whenever we will perform the onlooker B phase for the fifth solution, so all the 5 food sources has been exhausted because before it only it has exploited the fifth solution, right? So again it will come back to the first solution for the next onlooker B. So only 4 B's have been underwent the onlooker B phase. So fifth is pending. So it will start from the solution X1. Okay, so there is a chance that it will exploit the food source 1 again, right? So how to determine whether it can exploit the food source 1 or not? So again, it will select a random number R, 0.041. So as this 0.41, this is the probability of the solution 1.5. It is less than. So it is exploiting the solution X1, and now the X1 will undergo the onlooker B phase to generate X1 dash, right? If this random number is greater than P1, right? So again, it will start to explore the food source 2. Like that, it will continue, right? So as here we are generating 0.41, this is less than the 0.5. So the new value will be xj plus 5 into old value minus the partner value, right? So let us assume. So these things you can verify for one, you can do the hand calculation so that you can understand, right? Your variable 1 we want to change. Random partner is 2, phi is minus 0.87. Then you do these things, right? So what will happen here? Again, you will get a good solution here. That means when the fifth solution, for the fifth solution, you are doing the onlooker B phase, it is exploiting the food source 1, and after doing the onlooker B phase, it is generating X1 dash, which is better. This is better, right? So better means you have to reset the trial counter as 0. And with respect to this point, it is better, right? This point we are changing because we have considered the variable is 1. First bit we are changing. Okay. So it completed the onlooker B phase for the fifth solution. Now the onlooker B phase for the ABC algorithm is over, right? So we have done the employee B phase. After doing the employee B phase, we have modified some of the bits of the sum of the solutions, and after doing the onlooker B phase, we have modified some of the solutions. So we have started with 5 random solutions. After performing the employee B phase, again we got 5 solutions, right? And after doing the what you call the onlooker B phase, again we are getting the 5 solutions, right? Now what we have to do, right? So what we have observed during the employee B phase and the onlooker B phase, a food source may or may not generate a new solution. That means whenever a new solution we are doing that mutation, right? We may get a new solution or we may not get a new solution, because there is a chance that we may reach towards the global optimum solution, right? So we may get, we may not get also. So this is the population after performing the onlooker B phase, right? Next, what is the third phase? Third phase is our scout B phase, right? So whether we have to go for the scout B phase or not, right? So how to determine that one? So limit value we have considered as the 1. For simplicity, I have considered 1, right? So I have to check in the population after the onlooker B phase, which solution has trial value greater than limit, right? If you observe this here, this one, the third solution 0315, right? Its trial value is 2, which is greater than your limit value, right? So this is the abandoned solution. So this solution we have to replace. And if you observe here, right, what happens, because everything is random here, right? Randomness is there. If you observe, this is also the best solution, right? So always it will not happen that the best solution you are removing. So if you remove the best solution, you are losing that optimum value, right? So for that, whenever you are doing the scout solution, if any abandoned solution you are getting, so abandoned solution, how to determine? Its trial value should be greater than the limit, right? So what will happen? Because we are doing for one iteration and the small limit value, that's why we are getting this one, right? So this solution we have to replace. And we are observing here that this is the best solution also among this one, right? As this is a minimization problem, this is the best solution. So you have to memorize the best solution after the onlooker B phase also. That means whenever you are going for the scout B phase, you have to memorize the which one that is the best function, so that you will not lose that information in the next iteration, because every iteration you are updating the best solution or the optimum solution, right? So in the scout B phase, whatever I told, so this phase may or may not happen. It depends upon the limit value, right? So the solutions for which the trial value is greater than the limit value, that phase, if that condition arises, then only you have to go for the scout B phase. So here it is coming. So we have to go for the scout B phase, right? So scout B phase, what we have to do? We have to replace this one, right? If you are replacing, we have to keep something instead of 0315, right? So how to do that one? That will be selected randomly, right? So you are memorizing the best solution in the scout B phase. So why you are memorizing the best solution? So that we will not lose the best solution in every iteration, right? So you are storing the best population member. I mean the best solution, you can write here, best solution, right? And its objective function value, right? So this is the fit. Objective value is 35, fit is 0.0278. So what you have to do, you are selecting this one, because why you are selecting? This trial of this solution is 2, which is greater than your limit value 1, right? So next what you have to do, you are replacing this third solution, right? So this is the abandoned solution. So you have to replace X3 with a new random solution. So how to generate that random solution? LB plus UB minus LB into rand. So that is the random number in the range 0 to 1, which follows the uniform distribution, right? So by using this equation, you can generate a new solution. That new solution you have to keep instead of X3, right? So here, okay. So here, if you apply this one and then depending on the random number, suppose we are getting this solution, right? So here you are observing that all the bits are changing here, right? Previously it was, what is that? 0315, na? Previously it was 0315. Now this is replaced by this solution. 9.94. Randomly only we are doing, right? 9.71, 8, 6.0. So it may happen that we are generating randomly a good solution also, right? So what you have to do for this trial value, you have to fix them, right? Because its trial is 2 here and we are replacing this one. Whenever we are replacing this with a new one, we have to reset the trial value of the third equation as 0. So that is the here. So there is no greedy selection here. Simply you have to reset the trial value of that newly generated solution as 0. Inferior solution also you are accepting. At the meantime, you are not losing any information because you are memorizing the best solution in every iteration, right? So with this, if you apply, right, what will happen? You have generated, we have started from the initial population, right? We got this one, this one, this one, this one, and this is the abundant solution we got, and randomly we have generated this solution now. The trial counter we have kept as 0, but the remaining, if you see, this is 1 is there because this solution in the first iteration undergo the onlooker V phase, and there is a failure to generate a good solution, right? So what is the use of this trial? This is keeping track of how many times the solution is unable to generate a good solution. It went employee V phase or it went onlooker V phase, but that many times the solution is not able to generate a good solution. That means we are not able to explore better solution from that point. That is the meaning, right? So with this, the first iteration of ABC algorithm completed, right? Now you have started from a 5 population size, right? 5 solutions, and at the end you are getting another solution here, right? I mean another population. So same thing you have to repeat by considering this population, right? So you have to repeat these steps until your termination criteria is reached, and you know what are the termination criteria you have to consider, because so many optimization algorithms we have discussed so far. So simply consider the number of termination criteria as the number of iterations, or there is no change in the objective value. It depends upon you, and some threshold value. It depends upon which problem you are solving and what termination criteria you are fixing for your problem. Right? So the same thing you are repeating for a number of times, right, until your termination criteria is reached. And suppose after your termination criteria is reached, you are getting this population. Assume you are getting this table only, right? So if you are getting this table, whichever is best, because you are memorizing the best solution in every iteration, right? So that will be your optimum solution for the ABC algorithm, right? For that particular problem. So with this, the basic, right? Basic concept of ABC algorithm is over. If you are having any doubt with respect to this one, you please ask. Otherwise, I will go for the demo in the MATLAB code.
Please go for the demo.
Okay. Just give me 2 minutes.
Okay, ma'am.
Okay. After 2 minutes, I will start. Yes. So this is the ABC code actually here. What is the objective function is? Objective function is 1 minute. So here the ABC algorithm, this is written for training a neural network, right? If you are having knowledge about the artificial neural network, suppose this is my input layer having 3 neurons, and suppose one hidden layer is there, 3 neurons are there, one output layer is there, right? Suppose this is my 3 inputs, x1, or simply I will convert it to 2 input because that is a XOR gate is written. Okay. 2 inputs are there, x1, x2. This is one hidden layer. So this is connected to these neurons. This is the interconnection among the neurons. Right? This is the output. So this is a simple feed forward neural network where we have to train this neural network for one XOR gate, right? If you know the XOR gate, right? If there are 2 inputs, x1 and x2, what is the output? If this is 0, 0, this is 0, this is 0, 1, 1. Either one of the input is 1. This is 1, 1 means 0. So we want to train the neural network for these things. This is the training instances, right? So this is a simple ANN architecture. So when you will train the neural network, right, we are having the standard backpropagation algorithm, right? Backpropagation algorithm. So instead of the backpropagation algorithm, right, because in the backpropagation algorithm, if you see, there are lots of derivation you have to do, right? So that sigmoid function, whatever you are using, it should be right. You will be able to find out the derivative of that function, right? And sometimes backpropagation also, it may stop at a local optimum problem. So in order to solve that problem, you can train this ANN by using the ABC algorithm. Any optimization algorithm you can use for training the neural network. So your training means what you are basically you want to do. If you do the complete structure, there are biases, right? Bias 1, bias 2. Here the bias. These are the biases present in the ANN. So these are the weights. Weights. This is the weight. This is the weight. This is the weight. This is the weight. So your training means what you are trying to do. You are trying to find out the optimized value of these weights and the biases, right? So your target is to minimize the error. So error, how you have to find out? Suppose your actual output is 0, and whenever you are providing 0, 0, suppose you are getting 0.3. So what is the error now? 0 minus 0.3, actual minus predicted, right? So there are different measures are there. Your mean squared error is there, right? Root mean square, MME, different measures are there. So those measures you can use as the fitness function because you are trying to minimize the error whenever you are training the neural network. So you are trying to minimizing the error means you are trying to find out the optimal value of these weights and the biases of the neural network. So this optimization we have to do by using the ABC algorithm, right? Now what is the solution? What is the dimension of this given problem? If you want to solve this problem by using the ABC algorithm, right, we have to generate the dimension. This is the dimension of the problem. But how many dimensions? We want 1, 2, 3, 4, 5, 6. 6 weights. So I can write W1, W2, W3, W4, W5, W6. And how many biases are there? 3 as you. B1, this is also B. B1, B2, B3. So the dimension of the given problem is 9. So these values we want to optimize so that whatever your network, your neural network will produce the output that is close to the actual output. So this is our target. This is the optimization problem. So same thing, right? Instead of the 4 decision variables we have considered there, now your decision variables are 9. And what is the fitness value here? Fitness value is whatever the network is producing the output minus, actual value. Actual value is suppose 0 and minus whatever the neural network is predicting the value. 0 minus that predicted value. So that is the error. So that is the fitness function for the ABC algorithm. Now, once you have formulated this one, now that is very simple. Whatever you have done in the ABC algorithm, same steps you have to do here. So, just 1 minute. So that this problem has been solved by using this code. Okay. So now let me go to here. So these are the parameters you see. Your how many swarm size is 50 here. So food number means how many employee bees and how many onlooker bee. That I told you, your NP by 2, right? So always it is a even number. Then suppose maximum number of generation cycle equals to 20. For 20 iteration, you have to solve the problem, right? So these are the parameters, general parameters for the ABC algorithm. Then this is the objective function. This function, right? We have to solve this problem only. So the objective function is written here in the NNN train XOR. This is written, right? So this is simple. For this, you have to know how the ANN algorithm works, right? So here inside this function, you can write your objective function, whatever you want to minimize or whatever you want to maximize, right? So for that, we have to define what are the hidden activation functions used in the hidden layer, what are the activation functions used in the output layer. So that is the code for this one. So instead of this function, you can write simply your sphere function, you can write, right? And you can call that sphere function and you can observe how it is working, right? For that, you have to change the variable size there. Okay. So this part is for training the neural network. I mean, if you are providing the input to the neural network, depending upon the activation functions in the neural network, how it is providing the output. So this is the Y is the output for the neural network. So this log sigma, log sig, this is the activation function you are using in the network. Like your forward propagation only you have to do. You are not doing any backward propagation. Depending upon the W values, depending upon the inputs, depending upon the bias values, and depending upon the activation functions, you are predicting the output of the network, right? And what is the objective value? If you see that the mean square error is given, mean square error. So what is the actual value? This is the training out. What is the actual value? Minus Y, this is the predicted value, right? So that MAC value, that we are considering as the objective value. So what is our target? Our target is to minimize this value. This MAC value we have to minimize, right? So we are calling that function here. So we can use the sphere function here also. And depending upon the sphere function, only you have to change the dimensions here, right? So here the number of parameters, whatever simple architecture we have considered. So the number of parameters, this equals to 9. So if you use the sphere function, you have to change the number of parameters here. So this is the upper bound for the variables, each of the variable. This is the lower bound for the each of the variables. So you can write in different ways, right? LB equals to 0, 0, 0 for the 9 decision variables also you can write. It depends upon you. And the limit value I told you, limit will be food number into D. This is the how many number of employees you are using into the dimension of the problem. So for the one time only we will run the algorithm and we will see how it is minimizing the error of the neural network, right? So this is the global mean where we are storing the optimum result, right? Now let us, what we have to do? We have to generate, right? We have to generate the initial solutions. Your NP size is given, right? So randomly you have to generate NP by 2 number of solutions. So depending upon the lower bound and the upper bound, we are generating these random solutions. Right? For those random solutions, you remember the table. Then we have calculated the objective value of each function. So for that calculating the objective value, you have to call that function, right? OBJ function. That is the problem, that neural network train. You have to call that function. Okay. Next, you calculate the fitness value. Depending upon the objective value, you will get the fitness value of the individual solution. Next, what we have done, we have reset the trial counter to 0 for every solution. So this is the trial counter we have reset to 0, right? Then what we are doing in every iteration, we are memorizing the best food source, right? So you can find out initially the best find solution. You can find out from the first iteration, whatever solution you are generating randomly, because that value we are going to change. Right? So the global mean, this will contain the optimum value, and global parameter means this will contain the values of the decision variables for which your objective value is minimum, right? So these are the parameters we have defined. Now what we have to do? We have to iterate the procedure up to maximum number of cycles. That means suppose that is our termination criteria, right? So what now, once we have initialized everything, we have to perform the employee B phase, right? So employee B phase we have to perform for every solutions of the population, right? So for I equals to 1 to food number for all the populations, what we are doing exactly, right? So what we are doing for first solution, which decision variable or which parameter we want to change, because here I told you this is the right 9 variables are there, W1 to W6, B1 to B3. So which parameter you want to change, whether W1 to W6 or B1 to B3. So that parameter randomly, that variable you have to choose here. Next, what you have to do, you have to choose a partner for mutation. So this is the randomly you have to choose a partner from the remaining, right? Then that random should be different from the current solution, right? Then once you have defined that one, then if you have used that mutation operator, right, the new solutions, right, the solutions jth bit or the random bit will be the old solution, okay, plus that what you call that phi into the current solution minus the partner solution. So for that, this is the function we have written, or this is the statement we have written to do the mutation, right? After that, what we have doing, after doing the mutation, right, we have to do the bounding. If it is coming beyond the UV or LV, we have to forcefully make it to LV or UV. So this part is for if the bounding, corner bounding you are doing here, right? We have to check the bounds, upper bound and the lower bound of the newly generated solution, right? Then what you have to do, you have to evaluate the new solution, because you have to do the greedy selection between the current solution and the solution generated after doing the employee B phase, right? So for that, we have to find out its objective value. Then we have to find out the fitness value, right? Next, what we have to do, we have to do the greedy selection between the current solution and whatever the mutant solution we got after doing that mutation. So you have to compare the fitness value of the new with the old one. If the new one is better, so what you have to do? You have to reset the trial counter of that solution equals to 0. And fitness also you have to change here, right? Else what you have to do, if the new solution is not better, you have to increment the trial value by 1. So with this, you have performed the employee V phase for all the solutions in the problem, right? So this is all about your employee V phase. So next part will come for your onlooker V phase. So in the onlooker V phase, first you have to calculate the probability, right? So this is the probability you have to calculate. This is the matrix where you have stored, right, the probability value of all the solutions, right? So the formula I have used to calculate the probability. Then for onlooker V phase, right? So onlooker V phase, if you remember that pseudocode, right? We have to start from the first food source, right? So I equals to 1. And this is for counting, right? Which food sources are undergoing onlooker V phase. That's why your T equals to 0, because we have to start from the first onlooker V with the first solution, right? So while T less than equals to food number, because for every solutions we have to perform the onlooker V phase and we have to generate a new solution. That's why while T less than food number, how we are doing? We are generating a random number, right? If the random number is less than probability of that solution, ith solution, right? Then what we are doing? We are changing T equals to T plus 1, because initially this is 0. So what we are getting, we have to go for the next one. So again, we have to do that same thing, whatever we have written for the employee V phase, everything we have to write here, right? You have to find out which parameter, which decision variable you have to change, right? Then you have to write out the right partner, right? And you have to see that partner should be different from the current solution, right? Or you can combine this thing, you can combine the single statement also, you can write like the D we have written, right? Then you write it the mathematical expression for the mutation, right? Then you do the bounding for that mutation, same thing, whatever is there in the employee V phase, same part is repeated here. Then you evaluate the new solution by calculating its objective value and the fitness value. Then you perform the greedy selection. So after performing the greedy selection, right, if the on solution generated new solution is better than the old one, you keep the reset the trial value equals to 1. Otherwise, you are incrementing the trial value equals to 1. So with that, you are ending for that one, right? After that, what you are doing, you are incrementing the food source by 1, right? If the food source, right, if equals to I equals the maximum food source, what you have to do? You are initializing the food source again to 1, right? So with this, you have to perform the onlooker V phase for the solution, whatever solutions you have generated, right? Next, what you have to do, so limit value you have considered something, right? So what you have to do before doing the scout B phase, you have to memorize the best food source. So whichever is minimum, as this is a minimization problem, whichever is minimum, that minimum value you have to store in the global mean, okay? And that global parameters, that means those W1 to W6 and B1 to B3 values you have to store in the global parameters, right? With this, your onlooker B phase is over. Then your scout B phase, what you have to do in the scout B phase, you have to compare, right? So the trial of which solution is greater than the limit value, right? So it is the trial of indices. IND, it represents the indexes of the solution. It represents the limit, right? So that solution is the abundant solution. So what you have to do, you have to make that is 0, all the values. Then you have to replace that with a random solution. If you remember, that is LB plus UB minus LB into random. Then you calculate the objective function, objective solution, right? Then you calculate the fitness value, because you have to maintain that one for the next iteration, right? Then what you have to do, you have to, the trial value you have to initialize to 0. Right? The trial value also you have to initialize to 0, and the fitness value you have to maintain there, depending upon that, right? So after this is the iteration number it is showing, right? So at the end, what you are doing, you are finding the global mean. Global mean means whatever your best result you are memorizing in every iteration, right? That you have to update every step, and that will provide the optimum value of the given problem, right? So our target is to, and when our target is to what we are doing, we are minimizing the error while training the neural network, right? So minimizing the error means we are trying to find out the optimal values of the weights of the neural network, right? So you can change that one with the sphere function also, depending upon that parameter you can change. Now if you run this ABC algorithm, you can see, now you see every iteration the objective value it is showing. So objective value means only it is showing that MSE, mean squared value, right? So for 20 iterations we have run the program, and if you see, this was 0.18, right? So the MSE value, it is changing from 0.18 to 0.017, right? If you run this same program for a large number of iteration, and the population size also you can change, right? You will get better solution here. 1 minute, where the maximum number of cycles, this is for 20. Here if you change to suppose 100, if you run it, you can observe how you will get better solution. So only I am changing the number of iterations, so you can change the number of population also, right? Because we are starting from only 5 solutions, I think. So if you change that also, you may get better solution. This it is up to coming point 0.002, 0.001 now. So you keep some, right, higher number of iterations, population size also you keep some higher value. Now this is coming, right, 0.000 something like that it is coming. Right? So 0.0004 something it is coming, right? Like that you can change your objective function in this part. You can call that function, but here you have to change the dimension, right? As per the problem, you have to change the dimension of the given problem, and you can find out the solution for your optimization problem. Okay. So this ABC algorithm, right? There are binary version of ABC algorithm also. So discrete binary ABC algorithm is there. For feature selection, right? You can apply the discrete ABC algorithm, right? So their procedure is different because you have to scale all the values in the range 0 to 1, right? So for scaling 0 to 1, different algorithms are there. Discrete binary ABC is there. A modified discrete binary ABC is also there. You can go through those papers to relate this, right? This how this ABC, real coded ABC, and that's binary coded ABC. You can compare and you can check for this feature selection or instance selection for the machine learning problems. Okay. So that is all about your ABC algorithm. If you are having any doubt, anything, you please ask. So that's all from my side. Any doubt, any questions?